Minimize.
That's fine.
We're just gonna minimize this panel, hide video panel, hide floating meeting controls, and
Okay, hope everybody can hear me online, and welcome back. So today we have mostly practical. So basically we want to finish the assembly that we started yesterday. And we will start with the first step of the assembly process. That is really this overlap step. Now we generate the graph and try to find a path through the graph that define your final contigs. Hi, we just started. Of course, all this stuff is taken care of by software that was specifically designed for it. But we have reviewed now the basic principle how this works essentially. So we start the assembly, and in the meantime, while it's running, it's going to take a few minutes. Olivier will talk about HiFi reads, that is really the input that we provide to the assembler for this. Then we're going to review the scaffolding steps. So how you generate chromosome level assemblies out of this long contiguous sequence as you can get out of the HiFi reads. And we'll review, a couple of technologies that are involved and the sort of theory behind how you use this kind of data to scaffold the genome. And then we will, of course, scaffold our own genome in the practical. And hopefully we'll be able to also get into this manual curation, which is a final step where basically you want to use all the available data and software to basically manually check the assembly and see that everything checks out, or if there are some things you can correct, try to correct them. And of course, there is also QC throughout the assembly process. Now, every step of the way, you want to be able to check that thing went as expected. So we'll review that as well if you know.
All right, so thanks to everyone who's coming back today. So as Julia said, we're gonna get started with starting up HiFiAssembly, which was that software we mentioned last time. That's one of the ways we use to assemble HiFi reads. So that'll be done again on Galaxy. So give everyone like a second to log into your account, get your history set up, as I also switch my screen and get that set up as well. Let me see. Awesome. Okay. Want this. All right, so I've just pulled up my own Galaxy history. This is where we left off last time. As a little reminder, last time we left off just doing a lot of text parsing just to get some parameters that we'll understand more later on. So running HiFiAssembly is pretty easy, just like one simple step. So we're going to look for the tool called HiFiAssembly. Either one of them works, just click either one. Let me make this bigger so you can see. And then make sure the assembly mode standard, because HiFiAssembly can assemble either with just HiFi reads, or if you want to do trio partitioning to phase your haplotypes, that's one way of running it. We use that as well, but today we're just doing standard because we just have the HiFi reads of the individual. And you'll click data set collections again, and click on your HiFi data.
So trio is when you have parental data. You have something from the father and mother.
Yeah. To repeat for Zoom, Julia was just clarifying trios when you have paternal and maternal data to help phase the haplotypes, usually Illumina reads. Okay, so for options for purging duplicates, we're going to change this away from the default because the default's a pretty aggressive purging. And so in our workflow, we currently turn HiFiAssembly's internal purging off and we run purge dupes separately. So that's what we'll do today. So we're going to specify and just have like a very light level of purging. So that's this option. And then scroll all the way to the bottom for job resource parameters. We're gonna switch this, specify job resource parameters, leave the partition as VGL, and just put 16 cores. So 16. So each of our nodes has 32 cores. So this is just putting like 2 jobs per node, be a little quicker. But it should be about 10 minutes. and we'll hit execute. And you should see the history populates of four outputs from this one job. These are the GFAs, the actual assembly graphs that HiFiAssembly is producing, and we'll convert these to the FASTA file you guys saw yesterday, and we'll use that for QC and for all the scaffolding steps downstream. So while that's running, I'll turn this back over to Olivier real quick.
Everybody. Okay, fine.
You go.
Just wait.
Yeah.
So that people are not.
Yeah, I'll wait for a minute. That's okay. I'll go to the next slide now. I'll be right
So
back.
I'm going to be very brief. I think I can go faster than assembly. So, so I'm going to talk about the PacBio HiFi data. So yesterday I was mentioning and describing PacBio data. How the sequencing is very processive, the way the libraries are made with two hairpins on each side. So it's linear library, but topologically circular. And now we're going to see why it's very important for PacBio. Without it, PacBio will have an error rate, about 15% error rate. With this new HiFi data that they released 2 years ago now, the method, you can reach like a Q30 at least. Q30 means the quality value of 30 means that it's one error every 1,000 base pairs. So that's what the Illumina consider as perfect reads. Of course, when you have 100 base pairs, that's perfect read. When you have 20 KB, that's still 20 errors in 20 KB. All right, so HiFi reads again are nearly perfect. The way PacBio describe it is, let's not even consider the homopolymers. Threshold A's, because again, PacBio, like every other sequencers that have this non-stop sequencing, will have this problem for homopolymers because the data sensitivity will be compressed. So you don't know after 6 A's in a row if you have 7 or 10. That's a big problem for PacBio. So to assess quality, they just not consider these homopolymers. So for instance here, that's how they consider the almost perfect reads, is this series of 5 A's that represent 1 A, and then you get a perfect read. So there are some errors. But again, these errors are random. So with like assembly consensus, you can reach a very accurate answer. Let me move this. Can you? How do I? Okay, I don't know what to do. Okay, that's okay. So there is 2 ideas about Illumina versus PacBio. What you're looking for, Illumina, you're going to have high accuracy, but very short reads. And with PacBio, you have a low accuracy in general, but big chunk of data, very long reads. The problem of short reads, you get an incomplete picture of the genome, but with long reads, as Judo explains today, that where you can really be more accurate in the graph assembly and cover regions that you couldn't have done with short reads. So you have always, in the past, had to do a compromise between short reads and long traditional reads. And there was a constant battle between groups saying, oh no, I prefer short reads, it's cheaper and it's more accurate. But so there was a lot of arguments, but this argument now is resolved with PacBio HiFi data. Because HiFi reads can now combine these two. You get like reads that are at least as good as Illumina reads, but 20,000 times longer or 10,000 times, I don't know. Yeah, I need to do the math. 200 times, maybe. Thank you. You're the mathematician, right? So this is a marketing slide from PacBio where they describe, okay, where this new HiFi read is located in this landscape. So again, you have very high accuracy for relatively shorter read than traditional long reads from PacBio. So as I don't know if you remember, yesterday I was mentioning up to 50 KB or 50 KB reads in PacBio here because, as I'm going to show the next slide, the reason why you get HiFi reads very high quality is because you go around multiple times. So you cannot be 50 KB because your reads won't be long enough to go around multiple times. Yeah, I said that already. Okay, so on the top, on the bottom animation, you can see the CLR, the continuous long read sequencing, which is a traditional PacBio long reads. And you can see that the polymer is going around, but all you're recording is what they call the subreads. So this subread can be 50 KB, it could be 30 KB, and it's fine, but it has 15% error rate. On the top one, that's how you see the circular consensus, or HiFi, or CCS, they call it also, is generated. You go around, and instead of just considering subreads, you're going to combine the subreads and do a consensus of them. So because this error rate is random, 15%, what you're going to get a very high accuracy in the consensus. So you go around about 12 times, 10 to 12 times, and you get a Q, very high Q. So this is another graphic to show you exactly what I mean. So you have these two subread, the subread like the negative strand, positive strand, and you have the circular adapters become, the hairpin becoming circular, and then you go around multiple times. So you're going to get these very long sequence that's several dozens KB, and you trim adapters, and the consensus of that should be almost perfect read. Right? So it's very similar to the idea of on Illumina when you do a consensus of the cluster, right? You have the same library fragment on the same cluster, and what you see with Illumina, these high accuracy reads are not the raw reads. They're coming from a consensus of all the clusters somehow. The advantage of PacBio still remains. You have very little GC bias. So even with HiFi data, of course, you see the same constant coverage for all the GC, low GC, high GC, which is very valuable. Problem, there is still a little bit of biases, and I don't know if you will plan to address these biases later on. The GA bias. So there are some region of the genome that PacBio has a little bit more trouble to go through. They call the GA bias, GA, GGA, or whatever. But it's pretty minor compared to the GC bias in the webinar.
And it's just a template that polymerase.
Yeah, so when you do super long reads, the polymerase can struggle but fall off of this template because you're creating secondary structure or something, but you still get a long read, right? But for HiFi, because you have to go back and multiple times, you have more chance to fail, and then you fail and this read doesn't exist. So that's why you have a loss of coverage. I'm not doing, okay. So the mapability of these reads, not only because they're high quality, they're long, you can start to deconvolute some very difficult region of the genome, like you can identify transposable elements. You can differentiate repeats, because each repeat will have a small difference that you can capture now with these long reads, high quality. And phasing, and that's something we're using with the assembly. The phasing is crucial. Because if you, as Gio said yesterday, if you don't phase, the assembly will collapse into one haplotype. So you don't get any real representation of the genome, right? The two haplotypes will merge together, and then you get the wrong answer. but because HiFi are so long and accurate, you can walk through the graph and really split the haplotypes as Julia has a graph. I should have included this slide again. So that's the main advantage of that. And we see a big improvement in genome quality since we've been using HiFi. So one of the big advantages is you don't need to polish. So you're lucky here, you're going to use HiFi data, BioNano, and IC done. In the past, we had to polish it with Illumina data because the quality was too low. The advantage here, you don't have to polish, so you don't have any biases and compared with Illumina. And you assemble with like very high quality sequences. So this is how it looks like. I mean, I'm not sure I like this chart, but this is unphased assembly where the two haplotypes are merged together, but in reality, in this case, we have 4 haplotypes, like for a plant or something like that. So what you want to do is really separate them as much as you can. Yeah, that's all I have for HiFi. Do you have any questions? Yeah.
What's the state of the art you guys are using? Do you still use, like, if I were to give you a genome do today, would you just do HiFi with reads, or would you do a combination of HiFi with additional PacBio, or would you still use Illumina for polishing?
We don't use Illumina for polishing, but it's always good to have as to estimate the quality of your genome, right? This Illumina data is important. So you can estimate the real QV of your assembly if you have a data that hasn't been used in your genome, right? Yeah. But otherwise, just HiFi and IC, you get a beautiful genome. If you sample permits, so you have enough tissue, probably not in ants. You can do BioNano, but HiFi and IC is a gold standard. We start to explore ideas of using nanopore in addition to that, ultra-long nanopore. As you saw yesterday, the graph, that can help you to decide what is the path. Because now you have these long reads that can go through a long, complex path. So the job is obviously done by the sequences.
So for that independence of Illumina to help you give you a quality estimate, does that have to be run on the same sample?
Yeah, it has to be the same sample. Any questions online? Okay, so did I go faster than the assembly?
Let's see. You can close this real quick and I can peek at the cluster, see.
Well,
What?
Yours is finished.
Well, mine, yeah. I don't know if there's like, nope, everyone's done. Nothing's
Assembly
running.
beat me.
We wanted it running in a human time, so this is good. Okay. Yeah. So as you can see here, my assembly is done. So this is what everyone else's should also look like. You'll get these nice green jobs. So this is these outputs are the graph format, GFA, that we've been mentioning. Like, so they look a little different from the FASTA that we were looking at earlier or yesterday. So we need to convert these into FASTA so that all the tools downstream will use them, because right now not a lot of tools can operate on GFA. So it's just going to be a real quick conversion. And just on this slide, I have an illustration of like what this GFA looks like, actually, like when you visualize it in a tool that can do that. So it looks like these are all the nodes, and then you'll have some nodes that are connected by edges. And so these can't be represented very easily in linearized space. So when you convert to a FASTA, it'll just take the nodes and not the overlaps. So that's what we're going to do right now and convert it to FASTA with a tool called GFA to FASTA.
What are the overlaps?
The overlaps between the different nodes. So like, yeah.
represent the regions where there were multiple potential overlaps in the graph, so you couldn't decide where to go.
Like for
GFA, they're still represented as a graph. But because you cannot resolve them, you just drop all the overlaps. And
trying to find one that's like an easy path to like
Those
here.
Those can be interpreted as like heterozygous regions.
so usually they are big tangles of repeats that are very hard to resolve. If those regions, they nicely separate.
It'll be a cute little neat bubble where it's like homozygous, heterozygous bit, homozygous, and that's what the raw one looks like. So the raw one's a lot more messier than this. This is one that's already been simplified down. So like say you had one that's homozygous, little heterozygous, bio, homozygous. This one has already like called a path to walk. That's why they're so smooth on the top. But there are still some regions where the assembler's not really sure what the best way to walk is. So like for this one, or some circular regions are a little harder to see, but there's one at the end of there that might be like a repeat at the end that are not sure how the exact length of.
And another comment here, the reason why you have so many pieces is even in a graph space where you still should have overlaps with everything, is probably because you have some overlaps that were not found, like correctly defined, so they're not, the graph is disconnected. Either because the sequencing, simply because of sequencing randomly missing some of the regions, or because of bias in sequencing, or because of some problem with the alignments that fail to recognize some overlaps that exist in trees.
And so we chose the light for purge. How will that change the graph?
So for the purge duplicates, that's when we're making the primary and the alternate assembly. If we have the aggressive one, we're letting HiFiAssembly be like, these are definitely duplicates, and it's going to be a bit more of an even split. It's going to have more of even between the primary and alternate. Since we have only light, you'll see soon that the primary is like almost double the times, almost double the length of what we expect, because it didn't purge as much of those duplicates. So it's keeping a lot of those haplotyps and like heterozygous regions that should be represented only once in assembly. It's keeping them in the primary for now. And then we're going to take care of that later with purge dupes, because that gives us a little more control over like thresholds and where we want to call a duplication. So that's just the main difference with that. But if you leave it on, then it'll just try and do its best. But it was like not super good for a while, so we stayed with doing it separately. Right, so we can run a GFA to FASTA now. Do FASTA. It's this tool right here, and we can click this little two pages icon to select multiple data sets. And we just want to select our primary contact graph. And if you hold command or control, whatever you use, you get multiple selections on your computer. Hold that and then click on the alternate as well. So this is just telling GFA to FASTA to run on like both of these, so we don't have to run twice. And you'll hit execute. And this will be quick, and once it's finished, then we can rename it, just so that we don't get too confused about what it is. So. Yep. Waiting. Okay. I'll wait for everyone's to finish. I guess they all just ran at once, but. In the meantime, if yours is done, you can just go ahead and rename it. So you can tell like which one it is based off when it says data 31. So this is GFA to FASTA on data 31. That would be this one. We know that's the primary. Or let me refresh the page real quickly. If you click on the item in your history, there's this little data set peak. And so it'll tell you like the first, assuming it's not an ungodly binary file, it'll tell you the first few lines of your data set. And since this is a FASTA, we can see the sequence header and then some of the first few lines of sequence. If we look at both of them, we'll see one has PTG, another one's ATG. The P one is primary and the A is alternate. So you can go ahead and rename the one that's PTG, something like primary, contigs, FASTA, and vice versa for the alternate. Wait a minute to see if anything is still running. Be okay. Okay, I'm gonna move on to the QC steps now. So the first one, so right now I'm just gonna have you guys run the jobs just so that are all running in the cluster, and then we'll go over what it means, like how to interpret it. So right now it's just focus on just running the jobs, get it in the cluster and running while we're talking. So the first one we're gonna do is Mercury. And so this is this like reference-free k-mer based evaluation of our assemblies based on all the k-mers in the reads. So we need to feed it that Merrill database. This is a k-mer database from our reads that we made earlier, or like yesterday. And we have 2 assemblies, so we're gonna switch this over to 2 assemblies. And our first genome assembly, let's pick primary contigs. Second genome assembly, this is fine as alternate contigs. And the rest of this, just leave it alone. It's the defaults are fine. And we'll hit execute. And so while that's running, let's do, I'll leave this up for a minute, but yeah. Let me hit reruns so you can see it now. It's gonna generate, you'll see in the history, our QV stats. So this is when Olivia and Julia were saying that it's good to have an orthogonal technology such as Illumina. Right now, what we're using to evaluate the QV of our assembly is also HiFi data. So using Illumina would help, using a different sequencing technology would help get a more accurate estimate of your QV, since you're not using like the same k-mer data set you use to actually build the assembly. Like it's not circular anymore. The plots are going to be some spectra plots that I'll show you guys later on for how to interpret. And stats is like a completeness stats based, like how much of your reads are being reflected in your 2 assemblies. I'm going to move on to the next thing that we have to run. We're going to run this thing called bisco. It's a way of estimating the completeness of your assembly based on evolutionarily expected gene content. So bisco stands for benchmarking universal single copy orthologs. So there's these genes that you expect to be in certain taxa present at one copy, so not duplicated. And they're like usually housekeeping or somewhat essential. So you'd expect them to be in an assembly. Otherwise it would not be functional. So we'll do bisco. Click on that. And we're gonna analyze, we can do both of them, yeah. We'll do multiple data sets, and you'll click again with the multiple selection, either command or control on your computer. Click on both for your fastest. We're doing genome assemblies. Leave this like that. And for bisco can detect what sort of lineage it is based on the sequence. Like I guess it lasted. I'm not actually sure how it does that. We usually feed it and tell it what lineage to use. So we're gonna select lineage, and here we're gonna use Saccharomyces because this is a yeast. And last thing to change is in the outputs. So the outputs like a short summary of like the percentage of genes it finds, the percentage that are fragmented, et cetera, et cetera. We'll look at it in a bit, but I want you to also click this and then click on summary image because it's just a lot prettier to look at. So we want it to have the text as well as a summary image for us to look at. And hit execute. I'll leave this screen up for a minute. For our pipeline, we usually just have this set to vertebrata, but if you want to be more specific, they have a lot of other data sets for like ray fin fish, aves, stuff like that. Okay. I think that's good for now. We'll do, and then the last QC we have to do is just summary statistics. So getting stuff like the N50, average contig size. Oh, that's fun. What happened there? Let's see. Did I do this wrong?
And reach.
Does it not have internet? That's weird. Did you guys just fail as well?
Yeah.
Ah, it was going too well. Why? I did this before. Oh. Yeah. All the way to the bottom, right? Which one? These are all Pythons. Oops. Cannot reach HTTPS, yeah. Is it down? Let me, temporary little blip. Everyone trying to run it at once. Let's try, let me try again. I've run with Saccharomyces before. So I'm gonna just rerun that job real quick. We'll see. Sorry, we're doing it live. It's waiting to run. I don't know if it's sending that yet, though. Bisco. Oh.
Mine just, on day 34, general analysis. Alternate works. Just-
Yeah, I can't believe we DDoS the Bisco. Okay, so if it failed and it's red, so this is another, at least it gives me an opportunity to show you another, like one of the key things that Galaxy has. You can very easily rerun a job. So if you click on that item in your history, this little arrow circle, if you click that, run job again, it automatically has this all filled out all the parameters that you had before, and you can hit execute and it'll run it again. So, well, I just ran that twice.
Now it's running because it's
yeah, it's not like failing out immediately. Is this someone from ours?
yeah.
No, join Slack. Okay. You can have it locally. I feel like I did that for Vertebrate when I was running it on cluster, but I thought it would be okay. Sorry. Well, while this is possibly running and or not, if it doesn't, just keep rerunning it, which this is just like a internet issue, I guess, since it's just a server. And while it's running, we'll do the summary stats. It's this tool using QoS, which I forget what it's an abbreviation for, but it just reports a lot of those summary stats like average context size, N50, a plot of your context size distribution, GC content, stuff like that. So find a QoS. I'm going off of the tutorial and this was what was in it. So we click your two different ones. The answer was supposed to be for your question, Olivia. For reads, we can also, so QoS can like map your reads back for some other statistics. We can click on PacBio Smart Reads. And in our collections, so this is, I'm not sure why it doesn't like want to pick it up, but this is another tool of Galaxy. If your data set isn't in there, perhaps it's hidden, you can just drag it from the sidebar, like just click and hold and drag it in and it'll run with that. Type of assembly, this is the genome assembly. Use a reference genome, no, because we're gonna give it our estimated genome size from before. So you can search in your history on the sidebar, just type like estimated, then call it that. We not get this before? Okay, maybe we didn't. We did we not rename it? It's here, I just didn't rename mine. So perhaps you didn't either, but if you look in here, it might be called advanced cut on data 23 for you guys. It's just gonna be that haploid genome length we did before. If you wanna just copy it from here, go ahead. It's gonna be this number. So I'm just gonna copy that and paste it. An estimated reference genome size. That's what it's going to use to calculate NG50, which is again N50, but instead of using the sum of your sequences, you give it an estimate for it to use. And type of organism, this is a eukaryote. And the rest of this we leave, that's fine. Good to go. I'm gonna hit execute and just switch to the slide so that this info is here. And Busco, that was the failed ones. Okay, so my Buscos are good now. To clean things up, if you want, you can delete the failed ones. It's just a trash can icon. Spring cleaning. There is, yeah. One thing at a time. Okay, so those might be finished for you, maybe not.
Did it fail for someone again, or?
Well, I have a question.
What's up? Oh, it's too simple.
You had a question?
Sabrina. The assembly tutorial had lost.
Sorry, could you,
Oh, sure, yeah, sorry. There you go. Does anyone on Zoom want me to go back to any of the slides for like the parameters?
It's very touchy. I love it. Nobody else.
Okay, people are running Quast, people are running Busco, looking good.
Yeah, with Quast.
Quast, yeah, here.
Okay.
Julia, I think your section's next.
Okay, everybody's up to speed.
Make this a slideshow.
Here.
There you go, thanks.
Okay, so I'll just go over a few things, in almost random order. I mean, we already seen this. We already look at this kind of plots. You know, the genome scope plot on the left. You get these peaks that are determined by the level of heterozygosity of your sample. So in this case, we're looking at a very heterozygous sample. The haploid peak here, which is about half the total coverage, because again, it's stuff that is only present in one of the two haplotypes. Sometimes it could be because of the sex chromosomes. So there is only one representation of each sex chromosome in that particular individual. And then you have the diploid peak. We have the error k-mers that are at very low frequency, but there is a lot of them because every read has some few errors in it, and this will generate erroneous k-mers. And again, we can fit a model, a statistical model to this distribution to infer the genome size, heterozygosity, and so forth. If you look at the log scale, which is the same plot, but on the right, then basically you see the same thing, but now you can start also to see the high frequency k-mers. Sometimes you can see contaminants and other things like that. What we have just calculated with Mercury, and we'll see for the actual example, the value. Remember now we're talking about this QV concept, no? So that goes from 10 to, let's say, 100 in log scale again. So 1 error every 10 bases, 100,000, and so forth. So we'll see in a second the estimate of the QV that we get. And again, Mercury is using the k-mers to estimate the QV. So it's checking for all the k-mers that are seen in the assembly and asking the question, okay, so is this k-mers also seen in the row reads? Because if you see essentially a sequence in the assembly that is never seen in the row data, then there is a problem, right? And we made up that sequence, which can sometimes happen because remember now all these steps of the assembly process. Now, for instance, in the OLC graph, now you have to find the overlaps, create the graph, and then generate a final consensus. So if any of the algorithms throughout the process fail to generate the correct consensus, then you introduce k-mers that never existed before in the reads, but they're now seen in the assembly. So Mercury implemented an algorithm that will check the relationship between the assembly and the row reads for inconsistencies, and will output essentially the bases that show k-mer that are not consistent with the row reads. And then it will also give you a summary statistic that gives an overall average QV value for the assembly. Bisco, just a bit more details. So here is a report that looks like the one we will get out of our analysis. So in this case, we have just to have a few different examples, 5 different species. And you can see that there are different colors in the bar chart. So essentially, as Nell was saying, we tend to look for the number of complete genes. Okay, let me remind this. So the Bisco genes are sort of universal orthologous genes. So you expect them to see their housekeeping gene, something that normally the species won't be viable without. It's sometimes 3,000 genes, sometimes 300. Really depends on the taxon, on the lineage. It also, of course, not every. If you look at species that have diverged for quite some time, it's possible that we don't find that sort of housekeeping gene, or it has evolved so much that we don't really recognize it as such. But overall, we expect to see most of the Bisco gene present in an assembly. And of course, we also expect them to be complete. When it says fragmented, it means that, it could find some of it, but regions were missing or were disassembled, so not like next to each other. When it's duplicated, that's one of the biggest challenges still in genome assembly, that we tend to make the mistake and overrepresent the region of the genome. These has very bad consequences, for instance, when it comes to the analysis of the genomes, because there are genes that are, for instance, duplicated, and there are real duplications, there are gene families and so forth. So if you do not realize that the duplication was introduced as a result of an error in the assembly, then you may infer that these are actual real gene duplications. Or, for instance, when you try to map your reads, they will map to both copies, so you don't understand what's going on really. And duplication is easy because, again, we have sequencing errors. So sequencing errors tend to mimic real variation. And so if you don't recognize them as sequencing errors, you may infer, oh, there are 2 copies of this region, and then infer multiple gene duplication events. So we check for these duplications. In theory, Bisco genes should be single copy. That's not exactly true. Again, there could be real gene duplication in a particular lineage also of housekeeping genes. So that number is never 0, but it should be relatively low. And of course, missing. Okay, again, a housekeeping gene that is missing is weird. So if you take the first example, we have most complete, very few fragmented, a little bit of duplicated, that's suspicious, and a lot of missing. Here, the best one, of course, is number 3. Most of them are complete. There is none that is fragmented or duplicated, and few missing. And again, missing is also never 0 because there are also biases in how Bisco runs, and will maybe fail to identify genes that should be there, but for whatever reason, again, they may have diverged enough not to be recognized in that particular species. These Bisco genes are, of course, defined as of sort of abstractions for a clade, but they don't necessarily represent each species in that particular clade. This is a bit complicated as a plot, but it's very important. This is also a result from this tool that we just ran, so we'll see how it looks like for the East. It's a spectra plot or a K-mer multiplicity plot from Mercury. So it looks like a little bit like the histogram that we see for the geomscope plot, right? It's a histogram of K-mers as well, indeed. So the same x-axis, the same y-axis, but now there is a little bit more information here because we have an assembly available. So we're not just evaluating the reads as in the case of geomscope, but now we're complementing the assembly and the reads in the same plot. So basically what is really happening here is that we are coloring the k-mers of the previous histogram based on the occurrence and the count, essentially, of each k-mer in the assembly. So we compare the count of every k-mer in the assembly with the same count, the same k-mer count in the reads. So remember now, the shape of the previous is like, yeah, there is a descending line like this, and then it goes up, and then it goes up again, and then it goes down, right? This is not necessarily the same individual, so the heterozygosity could be different. But now we're coloring it. So this is telling us that k-mers that are, for instance, between 20 and 40 times represented in the row reads appear twice in the assembly. K-mers that are present between, let's say, 5 and 25 times in the reads are seen once in the assembly. And this is what we expect now, because again, if a particular sequence is represented, let's say about 30 times in the reads, given our coverage, our sequencing coverage, we expect it to be present about twice. Now it means that it's a sequence that is present in both haplotypes, essentially. So we expect 2 copies of it when we look at both haplotypes at the same time. When we compare, when we look instead to regions of the genome that even from the reads appear to be only present once, now they have a coverage that is about half the expectation. These, again, are usually sex chromosomes or heterozygous alleles in the genome. So we expect also to see them only represented once in the assembly because they represent the variation between the 2 haplotypes. So again, all good. And then everything that it's a very low frequency in the reads, as we said before, it's sequencing errors. So we do expect not to inherit this in the final assembly. And this is why it's black. It says read only. So we have essentially not included it in the final assembly. So this looks good. There is a little bit more sophistication about the 4 copy, but I will skip that. What is important here is this green small fraction here. So this is something that is 3 copies in the assembly, but if you look at its distribution, it's sort of peaking around 30, which is, again, as we said before, is where the diploid stuff should occur. So here it says, well, there are 3 copies in the assembly, but the reads only really support 2 of them. So this is usually the sign of having some false duplications in the assembly. And the reason why there is this purging step that we're going to go over now. So, well, there's this nice quote from the developer of one of these tools that use k-mers to analyze the genomes. If your spectra looks right, your assemblies could still be wrong, but if your spectra looks wrong, your assemblies cannot be right. So yeah, that's actually the case here. So we need to get rid of this green because it's really revealing of a problem.
That means it occurs 3 times in the assembly.
Yeah. Yeah. So it's 3 times in the assembly because it's green. So we colored it based on its counts in the genome, but in the reads, there is not really support for it because the number of k-mers that we have, the number of times we have seen the same k-mers in the reads supports 2 copies in the assembly.
Can you explain what it does exactly? What is different copy? Where is coming from?
So the different copy could be, for instance, that like as I was explained before, because of sequencing errors, you get the impression that there is an extra copy of something. So when you build the genome, the graph, and walk the graph, and so forth, you decide that the algorithm decides that there should be 3 copies and represent an extra copy based, for instance, on this Sometimes it's because we were always talking about errors, sequencing errors as an average. Now, like on average, there is that amount of sequencing errors, but it can happen that just by chance during sequencing there are a bit more errors introduced when reading a particular region. No, it's a stochastic fluctuation. So if that happens, then this fails to be recognized as an error because it's too high compared to what you would expect. So you say, oh, it's not errors. This must be something real because it's too high. That's one possibility. Make sense?
Well, I guess what's confusing to me, if it was duplicated in the assembly, why are there 4 copies of it in the assembly? Why just 3?
Oh, okay. Well, that's
It's only duplicated in the primary.
so it's duplicated in one of the either in the primary or in the alternate. Yeah, and that's. I mean, you could also have sometimes 4 copies as well. That would appear as this purple, but it would still be here if it's 4 copy in the assembly, but only 2 copies supported. It really depends on where and how the error was introduced in the first place, how many copies you get. But I would say it's generally easier to support an extra copy than supporting 2 extra copies. Now, if you think about it, that there is like a few sequencing errors supporting something extra, and you have normally 2 copies and you get 3, then, oh, there is 3 and then another unsupported copy for the same region. All right, so yeah, I mentioned this purging step because we want to get rid of them. I want to explain the details of this workflow, but the idea is that we want to identify those extra copies and get rid of them. Basically, we can use coverage analysis and try to identify them. And this is a tool that was implemented a few years ago that is really effective at this, Purge dupes. So basically, that's what you get. I just want to mention one last thing because we talked about trios before. So the best setup is always having a trio information. So if you have the parental information from the mother and the father, that's always the best possible scenario for any species because you can take advantage of the information in the mother and the father to basically understand better the haplotypes in the child. This is another kind of analysis that we're not going to run ourselves, these apmer blobs, but it's illustrating the power of having trio information when you reconstruct the haplotypes. So essentially, X and Y correspond to the 2 haplotypes, maternal and paternal. And these bubbles, they represent the actual haplotype, the actual contigs in your assembly. So the size is proportional to the size of the contigs now of the sequences that you have. And basically, we assigned the bubbles to each respective haplotypes. We give them an X and Y coordinate based on the information from the parents that we see that can be used to assign and infer whether they belong to the father or the mother. Now, because the father and the mother will be different, so we can use essentially their variation to assign the contigs. And this is sort of a setup where we know the ground truth. And so on the left, it's there's an assembler that can take advantage of the parental information. So you provide short Illumina reads to the assembler. And basically, you can completely separate the 2 haplotypes. So you can see that there are no bubbles that have a mixture of X and Y, a mixture of paternal and maternal paternal and maternal haplotypes. Whereas when you don't provide that kind of information here, you start to mix them. So that's and it's still a challenge. So there are now approaches, particularly that integrate these high-C reads, as we're going to see, that improve on that, but it's still an area of, let's say, problematic. This I will talk about later because we're going to generate this plot ourselves. But this is the IC heat map that essentially shows the IC information against the assembly and can be used for improving the reconstruction of the entire chromosomes. Yeah, I think that's it, no? So this is for later. Good? Any questions? Sorry. Questions online? No.
So, oh, yeah, so,
Yeah, I just realized that we are doing all the QC on the counties and not the scaffold.
We'll do-
We're going to do another round of QC.
yeah, once we get to the scaffolds. The Mercury, we don't do again because like stuff usually doesn't change that much, but Bisco might change and a lot of it's mostly just the assembly stats will be changing. So we'll run some of them after we finish scaffolding with BioNano and HiC. So right now we're just gonna check on the QC from the contagging step. So I have like the copy of what it should look like here, but I'll just show you how to like look at it in Galaxy as well real quickly, and then we can look at it on the slides because my explanations are on there. So if we click on our history, so these are the Mercury outputs are generated as collections. So you can click into it and then you'll have like these little ones. So this is the QV just for whatever you put in an assembly 1, 2, we want the one that's both of them together. So this one, your alternate is gonna be 0 because right now it's very small because we have purging set to light, so it really didn't put anything into the alternate. And I don't know what this would become. Oh, it's 83. So we usually aim for 60, right? Yeah, so this is like a good QV, but also it's synthetic data, and also it's usually inflated when you're evaluating it with HiFi K-mers. Yeah.
Very small genome, so
Yeah.
at this point in time, we can reconstruct it perfectly easily.
Glad we've made it that far in science. Yeah, this will like we usually for the actual like vertebrates I'm doing this on, we see something around like 60 now that we've moved to HiFi. It used to be around like 40s to 50s for CLR, 40 for CLR. So yes. And then
Is like 1 area. Wow.
so HiFi data. So the plots is like puts a bunch, but that's because it puts a whole bunch of different like plotting formats for however you want to visualize it. I prefer looking at the field one, which is what we we're looking at before, that just overlays it. So it'll look like this. I'm not gonna explain it just yet. I have them on the slides. So I'm just gonna show you guys like how you can open this. You can click on the view data button if you wanna see the plots, and you'll look at it like this. It can see it's pretty ugly. So, and then these are just the individual ones. I'll go more into that on the slides. For the Busco images, you can just click the summary image and it should pull up that whole neat little summary image that we looked at examples of before. You might notice there's a lot of duplication in this one. So this is the primary that currently has, since we didn't do any of that purging, or not a lot of it, it has essentially 2 copies of the yeast genome in one assembly. Similarly, if you click on your Busco run for the alternate, there's a whole bunch missing because you just have you have 5 contigs that are just like haplotigs that HiFiAssembly's light purging they were so obvious that even HiFiAssembly's light purging was able to detect them and put them into alternate. And the cost, I'll just show you what it looks like here, and also I'll keep this up because I don't have this in my slides. Yeah, it's a much different contig size, much different count of contigs, and you'll see the total length here is kind of the one I want to draw attention to. So our estimated genome size before was 11 meg. So this is 20 for the primary. So it's double the size. So this just supports what we saw in Busco, where it looks like there's another duplicated copy of the genome in this one assembly. Yes, I'm gonna go more in depth with the K-mer plots. Swap to here. I'm sharing my screen still, right? Yes, okay. So we will slideshow this. Okay, so more of these. So what should this actually look like? So the example that Julia showed earlier was the spectra copy number plot, which looks at both the haplotypes together. And so we're just gonna walk through like the first 3, the top 3. This is taken straight from the Mercury paper. The first one, Spectra CN, these are the read. This is what it looks like with reads only. So this is kind of, it's like what that geomscope plot looks like. This is the K-mer spectra that the reads are giving you before any coloring. We see our 1 copy, our 2 copy, and our what we know to be now our errors. And so Mercury, as Julie said, just colors them according to how many times that K-mer is seen in the assembly or assemblies. So in the copy number 1, this is looking at the 2 haplotypes together. So our 2 copy peaks, our 2 copy peak is colored in blue because these are seen twice. It'll be like once in one assembly, once in the other. And then the header 1 copy head peak is colored red for 1 copy. And these are our errors. And then the ASM one gives you a little more information about which assembly these K-mers are actually found in. So the 2 copy peak here should ideally be this green shared color because both assemblies should be having 1 copy each of these 2 copy regions because they're 2 copies together, but it's like 1 for each one and they're shared. That makes sense because these are the homozygous regions usually. And then the heterozygous portion, it should be usually evenly split unless there's a big sex chromosome difference. So for instance, the red haplotype, Cole, has this peak of K-mers that are unique only to Cole, whereas CVL has ones that are unique only to CVL. That's this blue peak. So this example is, yeah, this is a zebra finch example. This one's what this is what ours looks like. So this is like an ideal one afterwards, just an ideal example with real data. You'll see they're shared at the 2 copy, and then they're almost the same with a heterozygous peak, except one of them is a little bit higher, and this was a bird, this is a female bird. So there's the heterogametic sex in birds. So this is an expected difference. Like one of the haplotypes has the larger Z chromosome, the other one doesn't. Yes. And then ideally Bisco should look like this, which we looked at before as mostly single copy, a little bit of duplication, fragmentation, and missing, but it's almost all light blue. So this is ideally, this is just to give an idea of what we should be ideally looking for in our QC. And now, yeah. Sorry. Oh, these were just the the names of the parents in the trio canoe one. It's whatever was in the trio canoe one. Cow? Okay. Cows. Those are just the mom and dad cow. Yeah. Or strain, breed.
Yeah, breed.
Okay. So this is the example. Yes.
For a non-heterogametic species, would you expect even evenly sized?
They basically look the same.
Perfectly.
Yeah.
Because at that point, they are only K-mers that are generated from, let's say, SNPs or other polymorphisms. But then if there is a difference in one, it's like there should be a different K-mer in the other one. So maybe
just to repeat the question for Zoom, someone had asked about for homogametic species, homogametic sex, what this spectra ASM will look like. So this peak will basically, they'll mirror each other. They'll look basically the same if it's homogametic. And that's what we've been seeing. Okay. So this is what our actual use ones will look like. If you go ahead and open those in Galaxy, you can do that if you want, or you can just look at the slides. So our spectra's copy number looks pretty good. This looks similar to what we've been seeing with the het peak and the homozygous peak. Kind of, they're at where we expect 50x coverage, diploid coverage, 25x haploid coverage. But then our spectra ASM down here looks a little bit funky. And that's because you'll see, we want this to be shared. We want this diploid peak to be shared between the 2 haplotypes, because this is a homozygous region. They should be sharing these regions together. Some of it is shared between the primary and alternate, but a lot of it, all this red is only in the primary. So this is showing that these are uneven, 2 different uneven assemblies right now. And similarly, this is just a very big difference, even more so than would be attributable to sex chromosome differences. So this is telling us there's some work to be done with regard to evening these haplotypes out. And then these two plots, the primary spectra copy number and alternate spectra copy number, they're basically the same concept as this plot. They're just coloring k-mers according to the copy number in only one assembly. So spectra CN is both assemblies taken together. That's why that's why it's 2 copy at diploid and 1 copy at head. Oops. Whereas for this individual ones, it should be, you should see it like 1 copy across all of it, because it should be complete in a 1 haplotype. The fact that we see this blue 2 copy in primary means that there's 2 copies of these k-mers in their primary assembly, when there really should just be 1. So what we should be seeing after purging is we want to take some of these k-mers out and like put them in the alternate to get this more complete. Because the alternate, you'll see, has this like gray shadow behind it of read-only k-mers, and that's Mercury is calling it read-only right now because it's not seen in this assembly, but that doesn't mean it's not seen in the primary. So just because it's not an alternate doesn't mean it's not either. It means it's, so like in this case, it specifically means that it's in the primary. Sorry if that was confusing. What's up?
So to make sure I understand, in the primary spectra copy number graph, you're expecting to only see the haploid peak, basically.
The haploid peak and the diploid peak, but it'll be red because there'll be 1 copy. There's no duplicates.
The genome will be represented only once, so because it's just one haplotype.
Yeah, so this should ideally just all be red instead of, there shouldn't be anything that's 2 copy unless it's an actual gene duplication, and it wouldn't be all of this. So it should all be red. Okay. I also have the bisco plots here to give a little more of a more apparent visualization of duplication level. The primary bisco, as I mentioned before, almost half of it is present but duplicated, whereas an alternate one, a whole bunch of it is missing. So it just shows one is, the primary is not only complete, it's over complete because it has duplicates, and alternate is just not complete at all. So this purging, the way we do purging, seeks to rectify this by taking these haplotigs, the duplicated k-mers or sequences that are duplicated in the primary, and moving them into alternate to bring up the completeness of the alternate. Okay. Yeah.
What's the difference between primary and alternate?
So the primary one is it's the primary assembly that was generated by HiFiAssembly. That's kind of like the initial walk across the graphs. This is what it puts everything in first, and then any like obvious heterozygous or variation parts get put into the alternate instead. And so we had only light purging, so it didn't put a lot into the alternate. It's keeping a lot of it in the primary. So we'll seek to change or like fix that when we do purging. And okay. So the next couple slides, I'm going real quick just to show it's just a lot of follow the slides. I'll do it alongside as well, because this is the, it was the pipeline image that Julia had shown earlier. I'll go back real quick to it. We're going to do this pipeline on our assembly in order to purge it. So it's the coverage analysis, the self-homology mapping, and the actual like resolution of the haplotigs, actual taking them out of the primary and putting them into the alternate. And it's quite a few manual steps. Yes?
In the case of the, actually, maybe I'll ask the question.
Oh. Okay. I'm gonna pull these up side by side so I can do the, oops, here we go. Let's go back to Galaxy. Is this visible? Oops. Let me just fiddle around a bit with, I think this is okay. Okay. So the first step is collapse collection on our HiFi read. So remember how we have like a HiFi read, the whole collection of all our reads, you want them together in one file now. So this collapse collections tool should do this. Maybe I'll just search collapse. Where'd it go? One minute. Quick adminning. Sometimes the tools just don't want to show as installed for everybody. So let me make sure I have this. We'll do a quick uninstall and reinstall. And if you're, after this says like done, then refresh your page and I think it should show up. This is not something you're doing, sorry. This is like me as an admin trying to fix why this tool isn't showing up for everybody. Okay, let me refresh this page. Let's see. There we go, okay. So now if you refresh your page, then search for collapse, you'll find collapse collection. And you'll click that, move this in here. And we want to pick our HiFi data collection from before. So you have to click on this little folder icon, HiFi data, and that's all. And then hit execute. And we'll just rename it once it's finished. Mine's done, so I'm gonna go ahead and rename it to HiFi data collapsed. Save. And the first step is gonna be mapping our reads, this collapsed data set, to our contigs. So we'll look up map, and we have map with mini map 2. We click that. Okay, this one's got a couple steps. So the first one, we're gonna switch this to say use a genome from history, because we don't want to use a built-in one. We want to give it our FASTA from our history. So use a genome from history. And then for our use the following data set as a reference, we're gonna change this to our primary contigs, because we're mapping against our primary contigs. We're treating them as our reference sequence here. Single paired end, single, because these are smart reads. There's PacBio smart reads, which are single end. And then for select FASTQ data set, it should be just this HiFi data collapsed. Scroll down slow.
Just to understand, circular problem.
Sorry?
The same data was used to generate this, and we know we're mapping the same data back on.
Yeah,
Looks like.
to get like a coverage histogram of it, not hard, coverage pileup. Not sure what the best, yeah. Let's see. Okay.
We want to basically be able to distinguish regions that have normal coverage or our coverage.
Or 2 times, yeah. And the last thing two more things we need to change. For select a profile preset options, click on the drop down and just type in ASM5 and then click what comes up. These are very wordy descriptions. So click just type in ASM5 and you'll want this option.
Well, but that's just a shortcut, ASM5.
Yeah, 5%, yeah.
Predefined set for this data type.
Mm-hmm. This is like the mini map 2 parameter, yeah. And then one last thing. For set advanced output options, we don't want a BAM file. We want a PAF alignment format, P alignment format. Yeah. Okay, we want the PAF file. Yeah, it's just not, it's like a BAM, but different. Gives us a bit more different info to work with. And when that's all done, we can hit execute. And let's keep this on the side here. Yeah. So it's just, I'll highlight the section we're up to. We're up to this. I'll leave this up, but I'm just gonna rename mine and you should too. We're gonna rename this to reads match to, let's name it primary context. And I'll save that. Okay. Give it one more second. The next step is going to be this purge overlap step, which is, it's going to take your reads mapped to your contigs and do that sort of like coverage analysis to try and figure out the cutoffs of what we're going to be calling too little coverage, what's going to call too much coverage, what we're calling normal coverage. And some of it is going to also be informed by those parameters we got yesterday. So I'm going to look in the tool panel for purge overlaps. It's gonna be here. When you click it, so this is like a tool suite. So there's like a whole bunch of different functions. In the beginning, we just need this one. It should be selected already. It's the option that ends with cal cuts plus PBC stat. Click this. And then we only have one PAF file, so that should automatically be selected. And then in cal cuts options, just scroll down a bit. In here, we're going to be changing the transition between haploid and diploid and upper bound for read depth, because these are the two parameters we got yesterday from our genome scope, all that text parsing business. So we're going to go look in our history, or you can just copy it from mine. We're going to scroll down in our history to find those parameters. So here's the maximum depth. That's this upper bound. So this was going to be 114. And then for the transition between haploid and diploid, that's this transition parameter, which is 38. So I'll type in 38. And I'll just edit this on the slide in case anyone needs to catch up. I'll just put it here, 38 and 114. Okay, I'll leave this here while I run this. Leave all the output files checked. This is fine. Execute, leave the defaults checked is what I meant. And we'll make a couple of outputs. This is based on a couple files that are needed for purge overlaps later on, like the coverage file, a histogram, and actual cutoff values. We're just gonna rename them after this, just so it's easier to remember which one's which. When it finishes, I'm gonna rename this. So it already has PBC stat based coverage in it. So I'm just gonna delete that and just write primary at the end, because this was under primary assembly. And we can repeat that with all that, all three outputs from purge overlaps. Histogram plot, primary. Cal cuts, cutoff, primary. See, okay. So this is the first step, which was getting the actual coverage, getting actual like coverage alignments. The next step is going to be an like a self homology map using their actual contigs. So I'm going to go ahead and we're still in purge overlap. So if you still have it here, just click it again in the tools. And then we're going to change the function now because we already did the coverage calculation. So we want to split the FASTA by ends. So I think this is like for breaking up scaffolds into their constituent contigs. Right now we don't have ends. I think this is if you would wanted to do it on a scaffolded assembly per se, but we'll just do this so that it's getting the format it's expecting. So split FASTA, primary contigs FASTA, execute.
Wait, sorry, what is this?
Yeah. So it's supposed to be splitting the your FASTA file at like ends or gaps. So if you were perhaps trying to purge scaffolds, it'd be useful for that. I think we still do it here just because I think purge overlaps expects a certain like formatting in the header name downstream, because we don't have ends at this point. I mean, some assemblers make contigs with ends. I don't remember. We don't use those though. It's just one of the part of the processing. So I'm gonna rename mine to split FASTA primary. Just save that. We can put this primary. And then we're gonna do minimap 2 again. So we'll search minimap. and we're gonna feed it this FASTA. So again, we don't want to use a built-in genome index for Minimap. We want to give it a genome. So use a genome from history, and we want to give it the split FASTA. It's already selected, it's the most recent one. And then for select a profile of preset options, just type in self, and then it should come up with the option for constructing a self homology. That's just mapping all these contigs back against the contigs themselves. So with a certain amount of parameters, click self homology, and we just want to get, instead of advanced output options, just tell it to give us a PAF file again instead of a BAM. And then once that's ready, you can hit execute. I'll leave this up while it's running.
So this, sorry.
No, you're fine. But
What we're doing here is we're mapping the primary assembly against itself. What this will do.
Find like homologous regions across it. Yeah.
See duplicated.
And you'll get like actual boundaries too. Yeah, like it comes out as like actual contig, not contig, like coordinates. And I'll edit the name, and I'm gonna call it self homology map primary. Give it a second. Almost done with this one part. I'll go on to the next step, which is actually purging the actual assembly. Because all of this is the lead up to figure out which regions are supposed to be purged. So we're gonna go back to running purge overlaps. And the function that we now want, we're gonna click here and scroll down to purge dupes. This is the actual purging, exciting. Click purge dupes. For the input file, we want to use our self homology map. For the base level coverage file, we're gonna click that PBC stat base coverage primary file. For cutoffs, CalCuts cutoffs. And yes, that should be all the changeable parts. I'm gonna hit execute and highlight this part. Go. It's not showing it's highlighted. Oh, okay. Here we go. So this is just getting us, as you'll see, a bed file, which will give us the actual coordinates in the primary assembly and the reason that Purge wants to get rid of it. It'll like say haplotype or overlap or repeat or junk. I think contigs, regions that have too little coverage get just called junk. Like we can peek at it here. See, it's called haplotype, this 0 to 1 region. Okay. Hello. Okay. We're gonna rename this one primary purge dupes bed and just save that. And now we're gonna do this step here, which is running purge overlaps one more time. And we're gonna change the function to get sequences. The FASTA we're doing this on is our primary contigs. And the bed input is the one we just made, the primary purge dupes bed. So it's gonna go and look for these contigs and these regions, and then because it's a haplotype or overlap or a junk, it's gonna take them out and hit execute. I hate how it names it, but I'll show you guys something in a minute. Histories. Oops. Does anyone want me to go back to a different slide, or it's okay for now? This is what we're up to. Okay, so we have a chat. Okay, I'm paused. Second to catch up. While everyone's thing is running, I'm just going to show you something real quick. So back to the data set peaks. Galaxy shows you the first few lines, and since it's a FASTA, it's nice and visible. We have our sequence header and the actual sequence. And so Purge Dupes does this thing when it names it. This gets the haplotype. This is the stuff it took out of your primary. These are all the haplotypes and other like junk, overlap, etc. And it names it according to that reason that it took it out. Whereas if it stayed past the purging, it just gets this like _1 appended to the sequence name. So I'm just going to rename these. So for get-seq's haplotype, the one that's get-seq's haplotype, edit attributes, and we're going to call it haplotigs from primary. And once that's renamed, I'm also going to rename the purge sequences. So this is the one like your purged primary or post-purged primary. So I'm going to call this primary contigs purged. For a second, I'm still running. Oh, no one's running right now. And that's what purging the primary is like. So the next step is purging the alternate. So our pipeline has all these haplotigs. Remember how I said we're gonna take them out of the primary and put them in the alternate to try and bring it back up to expected completeness. That's gonna be the first step of the next part. So a lot of this is kind of the same stuff as before. The only difference is first we're gonna get that complete alternate contig set. So we're gonna do concatenate data sets. So search concatenate. And we want to have our initial alternate contigs. Where are they? So we have our alternate contigs, and we're going to add these haplotigs to them. So to insert data set, haplotigs from primary. And this is going to get us the data set that we're actually going to purge, and it'll become our final alternate after this.
So the haplotigs, just
yeah.
primary are basically duplicates purged from the primary assembly.
Yeah.
So now we know they ought to belong in the alternate assembly.
Yeah.
So
Yes. And then we're just going to do one more purge on it in case there's other stuff, or in case there's some like repeat content in the alternate that we don't want either. But we want to have these haplotigs in there because they ought to have been there to begin with. So this is just getting that data set up to a more complete state. We'll execute that. And the rest of these steps are essentially the same as before, but when you rename them, you're operating on the alternate, and you're also going to rename them as such. So if you want to go ahead and like do this part, I'll leave it up, but I'll walk through the steps still. So this concatenate data sets output, I'm just going to rename it so I know what it is. This is going to be called alternate contigs flow, and save that. And so this just the same stuff as before. We're going to do minimap to minimap to pick a genome history. And instead of doing the primary, we're going to be doing an alternate contigs full. This is what we're aligning our reads to this time. So single, and our FASTQ data set is going to be our, click this, HiFi data collapsed. So you'll have to scroll a little bit to get it. And again, the profile, when you click on profile options, just type in ASM5 to pull up this expected high similarity preset, yeah. And then advanced options, don't forget to ask for a PAF file. Scroll slowly, execute. I'm just gonna highlight, this is what we're doing. That's what's running here. Okay, mine's done, so I'm just gonna rename it. Gonna rename it reads mapped to contigs alternate, just so that I don't get confused in my history because you already have the reads mapped from the primary. So I'm gonna call this one alternate. All right, and then we have to get the coverage calculations again, and that's gonna be in Purge overlaps. And it's this first setting, so that's fine. And PAF file is going to be a reads mapped to contigs alternate. And for calculs options, we don't need a the transition is going to be different because it's going to have a different profile for the alternate. But we can still keep the same upper bound because anything above 114 still counts as a repeat. I think it was 114.
Yeah.
Okay. So I'll type in 114 and hit execute. I'm going to write that here. Highlight this.
You guys ever use lower bound?
That's the junk parameter, the junk cutoff. I think it defaults to 5 at this point. We set it to like, I think 2. Because nothing's going to have under that.
And the coverage, right?
Yeah, we lowered it after HiFi.
It's too high and we'll discard things that are real.
But if it's too low, you'll keep junk, but we don't get a lot of junk with HiFi. So
And so more coverage, you have more of the peak separated than you can. Definitely remove the-
yeah, because more coverage the further away the head peak is from that error bit of all the way to the beginning of the histograms.
It's nice to have the low depth for that reason.
It's nice to what, sorry?
It's nice to have the low read depth stuff because it helps you determine what's junk and what's happening.
I mean, the low read depth stuff will be there. It's just that when you have more actual coverage of what you want, it'll move further away. So it can more clearly ID what's error versus what's like real sequence. That's just that low coverage, yeah.
You mean like the haploid?
Yes, the haploid peak.
Haploid sequence.
Yes. No. Okay, I'm just going to rename these real quick. Just renaming the same way as before. PDC stat-based coverage. Renaming it the same as before, but putting alternate instead of primary. Skip to the next slide. Not skip, but go to the next slide.
Sorry, what
Yeah.
is the transition different?
There's transitions different because the histogram and the coverage looks a bit different for the alternate. So we don't want to use the same exact one as the primary one.
But that probably comes from the original, the three behavior
Mhm.
law.
That came from, yeah, it came from the original KCOV.
Why, I just didn't understand why alternate have different.
Because we're not really trying to purge any duplicates out of the alternate, I think, and that was my understanding. I don't know if I'm off base.
The histogram itself, the read depth of the histogram, the alternate only has a single.
Yeah, like it might make more sense if we look at the plot.
Because it should.
Yeah.
have very.
So this is what it looks like here. So, because if you kept the same transition parameter here, I think it would just get rid of everything. But we actually want to keep it here. Because this is what it looks like for the alternate.
So
Mhm.
actually, in the end, the alt only contain the haploid achieve.
Yeah.
But not all those who look like.
It should have some of the homozygous, that's fine, but the homozygous will not be like duplicated in here. Ideally. So we don't need to do this transition.
Yeah, my original question was why the transition is different from out. Right now, I think I don't understand. Like in the end, what's the goal of out file? It's should contain only the.
Yeah, so the output could be depend. Now we would like to ideally try to represent both haplotypes, primary and the output and the alternate haplotype as complete as possible. In this case, we usually only represent the regions of the other haplotypes that really diverge. So not like so not the homozygous parts.
I see. So the output is much smaller.
Yes.
Yeah, and like I find it kind of helpful to look at the histogram plots. So like this was the one for the primary, and here's our like transition cutoff. You can see like the clear difference between haploid and diploid in here, and then it just if you had that same thing here, it would not work as well for the alternate. There shouldn't be anything to purge in the alternate, yeah. Because the purging is getting rid of duplicates, but we shouldn't have duplicates in the alternate at this point. So we don't need to use the transition parameter. But we still want to keep this upper bound because anything that's above here would still be like super covered repeat. Does that make sense? Sorry. What do I say? History. Oops. What happened? Refresh. Okay. So I just renamed mine. That's where I left off on. Just gonna do here. So we just finishing up what was on this slide. And then the next one is that self-homology mapping and the actual like purging. We're almost done, I promise, with this part.
And usually the output is less important than the primary. If we're really aiming for a single haploid representation, the primary is sufficient. Yeah. But then, of course, trying to recover both haplotypes is desirable. So that's why we can try to achieve that in different ways.
So we'll do split FA again on your alternate context full and hit execute.
By the way, I just saw the USB go.
I just thought you were really into genome assembly. I'm renaming the split fast to alternate. Okay. Last one is Minimap 2. Who are we fighting? Who's the US fighting? Okay. Use a genome, sports ball. Use a genome from history. Okay, Minimap 2, use a genome from history. And we want the split FASTA because this is again just a self-homology step, but for the alternate. And then we're gonna go down to the profile and search self-homology again. Click that. And I think this should be a path file. Change this to PAF and hit execute. Yeah. Oops. I'll show you guys later the importance of workflows because we have workflows that basically containerize this whole step and runs it automatically before you think that I just sit around and do this all day. There are workflows for this, but I found it's useful to like go through it step by step. It helps you appreciate the workflow, but also really like grasp like what each step is doing within it. Well, for HiC, we're doing a workflow because that's a pain. Yeah. So for Minimap 2, I'm just going to rename this. This is a self-homology map alternate. Almost done, and there'll be a break soon. Don't worry. Okay, so this is just the last step of purging. This is actually getting the sequences we want to keep. So do purge overlaps, change the function, scroll down to purge dupes. Our input's going to be our alternate self-homology map. Base level coverage file is going to be that PBC stat base coverage alternate. Make sure you don't pick the primary one. Alternate cutoffs, Calcuts cutoff alternate. And yes, okay. We'll scroll to the bottom and hit execute. This again just gets us that bed file of whatever purge dupes is saying this shouldn't keep in assembly. That's the bed file that we use to actually take it out because bed files are coordinates.
Yeah, the bed file is a very simple file. It's just also
Yeah,
name of the elements.
yeah.
Start and finish.
If you want to take a look here, it has that Chrome or config start end, the reason we're removing it. And I don't remember what the fifth line, it's a comment line. I don't remember what purge dupes uses for it.
Because telling you which homology.
Oh, okay. Got it. I'm gonna rename it to alternate purge dupes bed and save that. All right, now that we have our bed file, we want to actually take those sequences out. So we're still in purge overlaps. Click that and we want the function called get sequences. It should be the last one in the list. And we're taking from our alternate contigs full. So the original alternate assembly plus the haplotigs we added to it. So pick that one for your FASTA file and your input is the alternate purge dupes bed. And execute. And then we can rename that and then run QC and then finally see what all the purging was for. Yeah, I was like, we're gonna run a QC and then have a break. Okay, is the food there?
There's no food outside, so don't worry.
It's on the way. I'm gonna just rename it real quick. Once yours is finished running, you can rename it. Bless you. So the one that's called get seeks haplotype, we're gonna call that haplotigs from alternate. Save that. And for the one that's called get seeks purge sequences, we're gonna name this alternate contigs purged. I'm just doing this like renaming step that's down here. Stay on the slide for a minute. Once this is finished, then we can do the QC that we did before, and then you'll be able to see like what purging actually does. So I just have all the QC steps here, and you can just run them one after each other. It's the same as before, except now, like for instance, Mercury is going to be a little more markedly different. Mercury, we want the same Merrill database because this is again just from the reads, so that's not going to change. We're doing 2 different assemblies. And so we want to look at our purged assemblies now. So for our first genome assembly, change this to primary contigs purged. And then for a second genome assembly, it should be the alternate contigs purged. And the rest of it stays as default. So I'll leave this up for a minute. Execute mine. So this is just going to help us see if we really did fix how the all those 2 copy k-mers that were in the primary assembly, did we actually get rid of them? And did we actually bring the completeness of the alternate assembly up? Are these actually getting more equivalent with each other, the way we want them to be? The other one we're going to do is bisco. So I'm just gonna have it run on the primary for now. This is fine. We can just run it on primary context purged. And so what we're expecting to see after purging is that we've gotten rid of a lot of duplication. So the previous bisco plot was mostly, it was like half dark blue, which meant a duplicated bisco gene. So ideally we should be seeing less of that now. So primary context purged. And again, we want to select the lineage as Saccharomyces. And we want a summary image. And execute that. And similar thing with cost. We're just going to run it very similarly to before, except we're just picking our here primary context purged, hold command or control, alternate context purged, and we don't have to do the reads, that's fine. And yes, and their alternate, not alternate, our estimated genome size. Scroll. Where did I put it? Here. I can also just copy it here. I'm just going to put this in the slide for anyone following along with that. Looks small. There we go. And just tell it it's a eukaryote because it is. And execute. And I think that's our, we can use this as a break time now while this is running, I think. And then we can like look back at the QC afterwards to see how it looks. Let me see if the not yet. So what do we do? Okay.
Can you just give a little like
Yeah.
60 seconds?
Yes. I'm leaving this up. Yeah. How much? What's that? What's consistent? Yeah, preferably you could do that because I also moved around some of those slides. Yeah, away from her. Sorry. Away from her schedule was confusing. Sorry. Where we lived, it's fine. Because I figured out because the next section is filtering. The scaffolding is going to be a lot quicker now because I'm not going to do my hand. Okay. Yeah. That will be. It'll just be
You can skip the tuition. You can explain that.
Like 225. What was it doing? It's what I figured. There we go. Hurting sucks. Well, I see now. Okay. Mhm.
I think I'm going to start looking at some of the QC now. Good with this? Okay. Keep this in. up some of those plots. I'm gonna start looking at some of the stuff now. I think. Yeah, what's up?
I follow through all the process, but could you explain the easier understandable word language actually which step is that?
Which step is what? Sorry.
What exactly each step is like?
Oh, sure. Yeah. Sorry.
I understand the high level that concept.
Sorry.
I don't know what order.
This is the number one, like in this slide. You mean?
Oh, no, I mean the whole purchase step.
Oh, sure. Yeah. Okay. So, like, it might be better if I have the image beside it. Let me copy this to something. Yeah, we'll just throw this into PowerPoint and then put it on the side and zoom in so that I can show it alongside the steps. Okay. So the first step was that read def analysis. That mapping reads to contigs here. Mapping reads and calculating coverage is the step in Minimap 2. Generating a coverage histogram and our base level coverage. That's these PVC stat base level coverage file and our histogram file. So that's all, the whole first steps were this read def analysis, mapping our reads.
So you mean the two peak plots that we just saw in the first QC?
Yeah, there was that makes that histogram plot that we saw, not from the first QC, but there's a lot of histograms, I'm sorry. Purge makes its own histogram plot. That's the one where we got to see the transition plotted against the actual coverage and also the upper read def bound. Let me pull that up. Oops. It's what makes this plot. Histogram plot primary. This is the one that Purge dupes makes. So this is our transition parameter from before. You can see it like clearly, pretty clearly that bisecting between haploid and diploid. And this is our upper read parameter, because anything above this, we're going to count as repeats. So this is made in the first steps of the Purge dupes pipeline. That's this coverage read def analysis. And then the self-homology map to find like homologous regions in the contigs that are like homologous to itself in the contigs. That's this all versus all self-alignment step.
Why do you
To find homologous regions that might be like duplicates, because they're like showing up more than once. Yeah.
So anything can be found suggest that is.
It could be a duplicate. Yeah, we'd have to look at the coverage as well to see how the reads are going against it. But it's just more evidence as well. And then the last step was resolution of haplotics and overlaps. This is like just actually getting the sequences from that contig file. So that's all this whole step at the bottom. So that's the pipeline all split up into step. Thank you for asking that. It would be good. I should have pulled up the plot, not a plot, the pipeline while doing this. But okay. I'm going to go back to our QC, our post-purging QC. So the first thing I'm going to look at, because it's easy, is bisco. So this is, you'll notice, looks a lot different from before. As we expected, we've lost a lot of this dark blue. And now it's instead all complete and single copy, or mostly that. So we've taken down the duplication level in the primary. Awesome. And then let's look at some Mercury plots. Super fun. Make this bigger. So the copy number stays the same basically, but if we look at the ASM plot, because that's the one that actually shows us the K-MERS assignments in the haplotypes, it's a lot closer. I mean, it's exactly what we want now. This homozygous peak is all shared now. Now it's our actual homozygous regions are split evenly across the primary and the alternate, giving us like together a complete picture. And the alternate is actually not just like nothing. It has its own representation of heterozygous regions and same with the primary. So this looks a lot like what we were aiming at. This is what a good K-mer, K-mer spectra ASM plot looks like. So that.
Just one quick comment here.
Yes.
If you are wondering why these plots, they don't look as smooth as, for instance, others that we've shown. One reason is, well, the counts are lower, no, because we are looking at yeast small genome. And the other reason is because it's simulated reads. And this speaks to the fact that really simulating real data is not as simple. So the tool that we use to simulate reads will tend to, the same thing over and over, even if it's.
So that's why this is like
random.
a little bit pointy compared to like the smooth peak in our example images, like the one I showed of the zebra finch. Yeah, just a little bit crunchy, but that's okay. And we'll quickly look at QUAST. So now we have, as a reminder, our expected genome size was about 11.7 meg. And the primary before purging was 20 meg, and now it's brought down to 12.2, and alternates brought up to 11.9. So these are a lot closer to what we're actually estimating for the genome size, what we're actually expecting for the genome size, which speaks again to the fact that we've taken out a lot of the duplication and brought up the completion in the alternate.
And going back to your previous question, the alternate is still a bit smaller, again, because we're not like necessarily representing everything.
Mhm.
However, we do represent variation in context. So we tend to see also the regions that are non-variable next to the polymorphism. Imagine you have a
Because it pulls
SNP.
down the homozygous set parts on the side.
Yeah, imagine you have a SNP. No, you're not going to just represent the SNP. You need to represent everything that's upstream and downstream. So there is more, but yeah.
So the way I had this set up was the next one. It's going to be viewed.
There is still no foot we're figuring out problems.
Okay.
But we're I think we can keep going.
We did, this is just what we did already. Post-purge QC. I did have slides on this.
We'll take a little extra time before.
I mean, our break is like in 5 minutes. Because the next thing I want you guys to run. So that was a lot of steps to get to like what we want QC wise. But recently HiFiAssembly has a new mode that allows you to integrate Hi-C reads from the same individual to phase the haplotypes instead of doing this like coverage based, not really guesswork, but like it's a little more imprecise. So Hi-C phasing will let you kind of right off the bat have nice phased, more complete haplotypes, because it uses the long range info to be like, oh, this SNP was on the same like long piece of DNA as the other one. So they belong to the same phase or the same assembly. So I'm just gonna have you guys run that real quick, and then we can look at the QC in a bit. So these are the steps. I'll pull up my Galaxy to do it alongside you. HiFiAssembly. Click this one. And so we'll still assembly standard mode. It's not a trio assembly. And then we're gonna go pick in our collections again, our HiFi data. Scroll down, and then for options for Hi-C partition, this is where we'll specify. For R1 reads, we'll pick our forward FASTQ. So that's the one ending in _1, and our reverse one ends in _2. And that's all we have to switch. Aside with job resource parameters, we'll specify, and that should be 16. And leave that to execute. It'll take like 12 minutes, which is why I was like, break time after this, but we'll see what I do. Any minute now. Oh, elevator. I can put on the soccer game if you want. What does that mean? Soccer. I don't know what I'm doing here. I'm gonna go back to the HiFiAssembly instructions for Zoom. There you go.
How does the accuracy of phasing using
Yeah. Okay. It's really quite good at preventing intra-contig switch errors, so that, on the blob plot we saw before, there were a lot of contigs that paternal and maternal hapmers within it. You're not going to get that with the Hi-C. From what we can tell, it's like a very little amount. So hap1 might still be like a whole maternal contact and a whole paternal contact, because there's just no way to assign them to the actual contacts themselves to different assemblies without the SNP info. But there's much less switch error. We found that with our zebrafinch data that like recapitulates very nicely, and they showed it with the human data in the paper.
And using the IC integration when you have the tissue availability, you just do it from the same individual.
Oh, yes, so obviously it has to be.
You can get close to a trio approach.
Yeah.
Yes.
It's like been game changing and much less, you'll see that like we don't have to do purging because it's not going to put out a duplicate because it knows what belongs to which haplotype. So we've switched to HiFiAssembly and Hi-C for all our assemblies so far.
Very cool.
Yeah.
How many cells do you need to clear out IC?
All these cells. I think about 2 to 3 million cells.
3 million.
Olivier is saying we need 2 to 3 million cells for Hi-C.
That's all much.
You're doing this with blood samples.
We do a lot of it.
So in the QC,
Yeah, and then they can see
and
it.
then we go through the scaffold.
And then it's like your scaffold, I'm not
Okay.
sure in the file. Yeah, no.
And the practical and then the curation.
Yes. Yeah, just vibe for now because this does take like 12 minutes to run.
So just for those on Zoom, we're in a couple of minutes, we're going to take a little break, 15, 20 minutes, and then resume with an explanation of how scaffolding works using Bionano and Hi-C data. And then we will have the practical on that, and the final bit is going to be on the manual curation.
Thank you.
Thanks so much. Okay, so cookies are here.
Okay, so we are back. It's still running, but I'm just gonna show you, we can queue up the jobs while it's running. Like we can tell it to use this as an input, even though that job is still running. So we're just gonna do that. So that it will be more timely. So what we're going to do, I'm gonna modify it a bit from here because the thing is you can't rename a job until it's finished, but you can still put it as an input. So we'll just do our best here. So search and tools for GFA to FASTA. Chat. And then we're gonna do some multiple data sets. So again, click the little multiple papers icon. And now we want to click on HAP1 and HAP2 contour graphs. And then you'll hit execute. And you'll see that these are waiting to run now because they're waiting for this one to finish. So one of these is our alternate, one of those, not alternate, sorry. One's HAP1 and one's HAP2. Since we're running all the QC on both of them anyway, it's fine, we can see it. They're gonna look the same. But, oh, HiFi hasn't finished, so that's fine. It just finished.
Yeah.
Cool. So yeah, everyone's is, I think, finishing up now. That's good. So we'll queue up the rest of it. Let's queue up Mercury. Mercury evaluate the assembly quality. This is still default and it's still our same camera reads. And now it's still 2 assemblies. And now we're gonna wanna do our HAP1 and HAP2. So I don't have them renamed right now. If yours finishes and you have the chance to, go ahead and rename them according to what they are. For instance, GFA to FASTA and data 115. This one's data 115. So this is hap 1. This one's data 116. So this is hap 2. Since we know that they're both like hap 1 and hap 2, it's fine if we just make sure we have 117 here and 118 here, like data number 117 and data number 118. And then we're good to go for that. This will queue up and run. We also want to run bisco. So navigate there, and we want to run it on both hap 1 and hap 2 again. So we want to do multiple data sets and click both of our GFA to FASTA outputs. And then our lineage is still Saccharomycetes. And we still do, oops, my text editor. We still do want to have our summary image. So this is all set to run bisco in those 2 files. Execute. Queued up to run. And then we have cost on both of them as well. So pull up cost, use a multiple selection again to click both of our GFA to FASTA. Click both of our GFA to FASTA outputs. Our estimated genome size. I should really write this down, but I'm just going to grab it here again. If you want to copy it from here, paste that in there. And then this is still a eukaryote, that hasn't changed. And we don't really look at the reads when we map them, so it's okay. We don't have to do this part. The rest of this stays the same. For quast, execute. Let's check on. Okay, everyone's HiFiAssembly looks to be done. So people's QC is running now. While it's running, I'll just show some of the results. Yes, what? Yeah. I was gonna show the Mercury ones, yeah. Let's split their screen so you guys can still see this and run all that. But we can, in the meantime, look at Mercury. The copy number plots look basically the same still. It just looks the same. And then, but now we'll see that our Spectra ASM looks basically exactly like what it looks like after purging and exactly what we want with this shared homozygous region above like 50x, which is our diploid coverage. And then the 2 neat heterozygous peaks for hap 1 and hap 2. Yeah, and this is kind of what a heterogametic one would look like. I'm not sure what the difference is in this yeast. I don't know yeast sex chromosomes.
Well, that's the thing.
Yeah, but for like our real data, this is what our like XY animals or our ZW birds end up looking like. If it's XX or ZZ, then this is basically just the same mirrored peak. So this just really shows the strength of using Hi-C phasing. We don't have to fiddle with any purging. We just have our nice phased haplotypes, nice complete assemblies right out the gate. I've had to purge maybe like once or twice in all of this.
It should be the same for a trio phase.
Sorry.
For a trio phase, you can also.
Yes.
And so
Yeah.
just one comment here that this also speaks to the fact that many of the duplications that we see are actually caused by failing to resolve the haplotypes. So when you have information that resolves the haplotypes, you don't get the duplications.
Trio and Hi-C data.
Could you explain how Hi-C data how use the
So it's just a long range. It might make more sense when we get the Hi-C. Yeah, because we have some Hi-C slides coming up. So I think it'll make more sense in that context. But basically the long range info helps you know what was on the same molecule. But, yeah. Bisco's still running, but we'll see. Oh, it's done. I'll refresh this and we can look at what it looks like. Here. It doesn't matter which one we look at because you'll see they look almost the same. You'll see that there's a bit more missing. That was because perhaps that little discrepancy between the hap1 and hap2 on the heterozygous part. This actually comes up when you're doing heterogametic specimens too, because the BISCO data set has some genes that are on the sex chromosome. So say you have like the, so you'll have the female of a mammal, or no, sorry. You have a male, and then the haplotype that happens to have the Y will have some genes marked as missing on BISCO because it doesn't have the X chromosome and it's looking for some genes on there. But overall, they're both complete. There's no like duplication to resolve. So that's great. And then when we look at QUAST, it's also very, basically almost similar to the primary and alternate stats from before. Nice even number of contigs between them. And also we're close to our estimated genome size of about 11 meg. So like right out the gate, it just looks a lot better and we don't have to do all of the work involved in purging. So the next slide would, okay, we're good in chat. So now, yeah. Generally, no. I've done like 10 to 15 maybe HiFiAssembly Hi-C ones. I've only had to purge like once. Yeah, but yeah, just like Trio data, there's just like no purging. I mean, I can introduce this one slide because it's so practical. So now that we're gonna work with this nicely phased hap1, hap2 contigs, and we're gonna scaffold it now. So this scaffolding part, what we have, so this is a genome, these were our reads. The HiFiAssembly step has put them together into these nice contiguous sequences. But now we want to actually scaffold them using some long range info, like this bio-nano optical maps or Hi-C contact information. So it's gonna link them together and like separate them by gaps. For bio-nano, you'll know what size they are. For our Hi-C methods, they usually use like 200 ends to gap them to as a gap of unknown size. So our first one we're gonna do is the bio-nano optical map. Yes.
Can you just point, if you go back to your course results? Quickly.
Yes.
So the Easter, it's an eukaryote with 16 chromosomes. And here we have 18, right? So there is something that is broken, and we broke it on purpose because otherwise this technology would resolve all the chromosomes in one piece with such a small genome. But to give you an idea that we're missing a link here, and that's what the scaffolding will allow us to recover.
So we're gonna work with this, the hap1, or whichever one happens to be your 18 contig one. We'll see next. This is the bio-nano scaffolding step. It's very straightforward. It's really like just these. So we're gonna look for bio-nano, hybrid, scaffold, and you're gonna have, so this is the only one where it like actually matters which one you select. There's two results here. There's one that has local in all caps. Click that one. And then to click that one. So I didn't rename mine because they queued it up, but when you click on the little data set peak, it'll say how many sequences are in the FASTA if my computer wants to scroll properly. A second. Okay. All right, you can see one of them has 17 sequences here. And then the other one, it should be the same for you. You'll have one of these FASTAs. One's gonna be 17 sequences, the other is 18. We want the 18 sequence one. So I will just take this and drag this here to NGS FASTA. And then, and if you did actually rename yours according to hap1 or hap2, this is hap1. And then we will have the bio-nano optical map. The CMAP is just that file format for optical map. We'll leave this here. Well, this is just configured according to what enzyme we use, which is I think DLE1 for all these at this point. We use some other ones in the past. True. I'm not sure. This is from Crystal. I think it's same one. Okay. But they have a couple other enzymes here in case you have a different prep. At the bottom, we have our conflict filters. These are just telling BioNano what to do when you have a conflict between what the optical map says and what your actual sequence contigs say. So we, in our pipeline, tell it not to cut or not to cut. We trust our contigs more. But for this, in this instance, we're gonna tell it to cut the contig at a conflict. And then we'll hit execute. And so that's gonna have 5 different outputs. So they're named very similarly, but the ones we're mainly interested in, well, there's a hybrid scaffold report we'll look at together. But what we're gonna be using later on is this NGS contigs scaffolded and then NGS contigs not scaffolded. So the one that's called scaffolded is the actual like hybrid scaffold, actual combination of the optical map and your sequence data. Whereas the one that's called not scaffolded is sometimes you'll have a contig that doesn't get mapped onto BioNano, and so it doesn't get scaffolded, but it's still like important data. It's still a contig that matters. So this is reported as a separate file, and we just have to concatenate them at the end of this. And while this is, okay, it's done. So this hybrid scaffold report is just a neat little report from BioNano about what it did. So it has your original statistics for the FASTA file that you gave it, our contigs basically. It's telling us there's 18 contigs. And then this, we want to see this hybrid scaffold FASTA plus not scaffolded. So this is the hybrid scaffold is what we call just the hybrid between the BioNano molecules and your sequencing contigs. So it's those scaffolded contigs plus anything that was not scaffolded. So we see this, the count has gone down to 17. So BioNano has managed to link 2 of the contigs together into one larger scaffold, and the rest of it got left alone, which is fine because, as Julio had said, we basically are approaching the actual chromosome count of this year. So this is usually a lot more dramatic on genomes that are a bit more complex in use, but it's still good that you can see that it went down. You're expecting to see contig count go down and then 50 go up because your assembly is getting more contiguous with the scaffolding, ideally. So the one last step before we do something else, we're going to, as I said, concatenate the data sets because we want both the hybrid scaffolds as well as the not scaffolded contigs. So the first data set is going to be NGS contig scaffold. And then the second data set is going to be NGS contigs not scaffolded. And we will just hit execute. And so this is basically what's that hybrid scaffold report gave us at the end, our hybrid scaffolds plus the not scaffolded one. So this should have 17 sequences in it. I'm just going to rename this to HAP1 BioNano. Sorry.
What did you trigger the catch?
It doesn't cut anything, so yeah. Okay. So now we have this. This is like in our pipeline. We didn't actually show an overall pipeline image, but this is what we usually refer to as S1, our like first scaffolds from BioNano. And this is what gets put towards HiC scaffolding, which is a very, very long process, but a lot of pre-processing. And I don't want to do that, so we're going to do a workflow instead. So if you go to this link here, I'm going to click on it, just so I have it in the side.
I think it's not Slack, right?
I just put it in front.
Thank you. Yeah, it's this link. Or just click it in Slack. Thanks to Cassie. all done with that. So we'll keep this big. Yet another HiC scaffolder is the name of the tool that we are using to scaffold. That's what it is. I don't know what salsa was named after, but okay, so that link opens to here. So you see this button that says raw. I want you to right click and click on copy link. And then we're gonna go to our Galaxy here and click on workflow at the top. Right now we don't have any, but we're gonna have one. So once you're in the workflow page, hit import. And then this free text box for workflow URL, just go ahead and paste in Command V, Control V, right click, whatever. Just paste in what was in your clipboard. And then import workflow. All right, and now we'll see that we have a new workflow, nice and imported. We can, you don't have to do this. I'm just, while people catch up, I'm gonna just show it to you so that you don't have to do this right now. Actually, it's more useful if you click on edit. This workflow looks like this, and it's gonna do all these steps for you basically. So we don't have to do it by hand because the HiC workflow is a lot of pre-processing, it's very involved. So you have to map the forward and reverse reads separately to your contigs, merge them, filter, sort, put that into pretext map, get a pretext snapshot out of that, put that into YAS, get your final scaffolds, and then align again to those to get another pretext map. So instead of doing that, we're just gonna use workflow. So now that you have that workflow imported, like when your workflow page looks like this, click this little play button or run workflow button. And oh, thank God, everything shows up. Okay. Yes, okay. Your scaffolded assembly is HAP1 BioNano. That's that concatenate job we just did. Our forward reads are the forward reads. Reverse reads are these reverse reads. And for your estimated genome size, so it's that file that we have before. You might have named it estimated genome size. I forgot to name it, so mine is called advanced cut. It's the parameter file that has the estimated genome size. We're gonna drag that into here. And when you hit run workflow, you'll see it's invoking that workflow and telling you how many jobs are being scheduled. And when it does that, you'll see your history populate with all these jobs that are being scheduled and set up and queued to run. So it's already started with the forward and reverse mapping, some of the parameter parsing, and then these are all waiting on this to finish. And when it finishes, you won't have to do anything. It'll just run automatically and run that workflow. So the gist is workflows are great. And I had it as a workflow also. It's a lot of pre-processing, but also two of these steps take like a decent amount of time. So I wanted to have this set up to run while the rest of the lecture happens, because perhaps some of it might finish by the time you leave, but if not, you can always just view it. And then the most pertinent things will probably be these pretext snapshots. I can like send a follow-up in the Slack about it. But that's essentially it for this practical part, unless we want to look at this later. The rest of this is just a scaffolding lecture. So I'm gonna put this back inside you.
All right, thank you so much, Linnell. Yeah, so do you have any questions? But yeah, go ahead.
Say I'm working on a different instance of Galaxy, but I would like to load this workflow. Can I just use that same link?
Yeah, I'll send you a different one because this one has a little bit configured for our cluster, but the ones that are like up in public are for like public ones. Like Delphi has a public GitHub that I modified those to work for our cluster.
Very cool.
Okay, so the questions? So I'll go over now briefly on how the principles behind this scaffolding approach using HiC. And then I hope we'll have enough time to go over a bit of manual curation. Okay. So again, the idea is that if we have a complex genome, then essentially we start to have a lot of repeats. No, if you think about vertebrates, the genome size can vary a lot. It can go from half a gig to 100 gig, and the main difference is just the presence of repeats. So they essentially introduce ambiguity in the reconstruction of the genome, and it cannot really be solved given the read length that we have, even with long reads in many cases. So basically, or we could have dropouts in sequencing that leads to a similar problem in a way, because essentially you don't have information to reconstruct a particular region. So again, you lose contiguity. So, over the years, there have been a lot of different approaches trying to solve this. Back in the day, one was, paired end reads, where essentially you could increase significantly the insert size so that you were sequencing on both ends of a particular DNA fragment. You were not able to read what was in between, but if in between there was actually the repeat, you could anchor two unique reads on both sides and sort of span the repeat with that kind of information. This is, it was used for a long time. It's still, there were other, made pairs, or you could do a lot of variations on this approach. It could be helpful a little bit, but essentially, still not resolving many of the repeats in complex genomes. Then we have something like called physical mapping. This goes back in the sort of pre-genomics era. Now you could essentially try to assign specific loci around the chromosomes, and then when you find the sequence, say, oh, well, this belongs to chromosome 5 because I know that that particular probe is on chromosome 5 from other evidence. This was actually generalized in BioNano, because BioNano, what it really does is creating this large restriction enzyme-based maps of the genome, so that you essentially have this pattern of restriction enzymes across the genome, and then you can compare your sequences to the pattern, because of course the sequencing is known, so that you can find in your sequence all the restriction enzyme sites, and then look at the pattern, compare them, and find essentially in the optical map where each particular sequence belongs. So here you can see, we have this specific pattern with 3 restriction enzymes in our contig, and means that it belongs here. Then here we have no sequence information for whatever reason, so we don't know how to place this. But then we have another contig, and again, we see if we orient it in the opposite orientation, we can match precisely this pattern on the optical map. And so we end up essentially reconstructing the order and orientation of the contigs along the chromosomes. And then we have this scaffolding with the contact data. And this was really originally developed for a different purpose, for looking at the 3D structure of the DNA of the chromatin in the cell nucleus, but it turns out actually you can really use it for reconstructing the genome sequence as well. So in the cell nucleus, the DNA, well, I'm sure it doesn't look like this, but the idea is that it's a sort of longer wire, and essentially the chromosomes, they are kind of separated from each other. So there is a space. If you think about a sort of a 3D structure, there is a space and compartmentalization, and there are boundaries between the chromosomes. So we can take advantage of this property because this essentially defines individual chromosomes in the 3D space. And if something is defined in the 3-dimensional space, now if we sort of idealize this 3-dimensional space and project it into 2 dimensions, so in the linear space of a single sequence, it's also defined, right? So we just remove one dimension. So the preparation of this HiC library is essentially taking advantage of this by first doing this cross-linking of the of the DNA, and essentially the cross-link captures these interactions at the level of the genome. So you have now, after you cross-link, you fragment and religate. So you see, you obtain these kind of small fragments of DNA, but they tend to belong to the same region of the DNA. And again, because chromosomes are separated in the 3D space of the cell, they will tend to belong to the same chromosome as well. And again, the point here is that if you measure the interaction frequencies, what happens is that you expect that the closer two sequences are in the 3D genome space, the more interactions you will see in your library. Now, when you start to sequence all these millions of small fragments after this library preparation, you expect a lot of interactions that are very close to each other. So that represent the regions of the genome that are close to each other to occur more and more frequently. There are some variation on this, but I'll move a little bit faster. So now we can represent these interactions in this kind of map. It's a heat map. So we have the sequences on both the X and Y axis, and you can see we're talking about the same sequence. So this is chromosome 1 and chromosome 1. So this means essentially the same chromosome against itself. And then we have chromosome 1 against chromosome 2, chromosome 1 against chromosome 3. So basically, the diagonal represent the cis interaction, everything against itself. And then off diagonal means trans interaction, so against the other chromosomes. So if we already have a genome and we map, our HiC library, again, because of this property of the HiC that derives from the way the chromosomes are packed in the cell nucleus, essentially we see that most of the signal belongs to the same chromosome and the other chromosomes are separated. And so again, this is even from an intuitive point of view, this tells us that we can take advantage of this information to reconstruct the entire chromosomes. And really, they are separated. So there are, few points of contact now in the cell nucleus, but there is very little. So how do we do this in practice? This is one of the softwares, but they tend to always work in the same way. They will be a bit more sophisticated or less sophisticated. Salsa 2, we have been using this for a long time. Now we switched to a new one. But again, they have better resolution. They do a few things differently, but the principle is always the same. So again, remember now we have these interaction frequencies genome-wide. Now we can say there is a lot of interaction here, a lot of interaction here, less interaction between, let's say, this region of chromosome 1, this region of chromosome 1 here and another region of chromosome 1 down here, which would be represented by something around this point, And if you project this from the diagonal. So here it would represent interaction between this position of chromosome 1 and this position of chromosome 1. And there is relatively little, so we take advantage of all this information, and we also produce some sort of graph using these frequencies. Okay, so essentially we have to represent the interactions between different contexts in this case. That could be represented by the nodes here. And we, of course, depending on how strong the interaction is, we can represent, let's say, more like a line that is more or less strong, let's say. And we represent all the interactions that are deduced from the HiC information. And then again, we need an algorithm. In this case, uses maximal matching algorithm that can simplify the graph to a linear form. Okay, so by finding the weakest interactions, pruning them, and resolving the graph into a linear form. So then we have, if we get to this linear form, it means that we have essentially a final linear sequence that represent potentially an entire chromosome. So we add original contigs, we added the interactions between them, we prune the ones that are weak, and we're left with a linear sequence that potentially represent the entire chromosome end to end, with some gaps in between, because the interactions, they measure physical distance, but they don't say anything about the sequence in between. Okay, so yeah, just to recap, again, these are the methods that exist for scaffolding. So paired end reads, not really useful anymore. Linked reads, we haven't been really talking about these during these days. They were popular if you just look at maybe 2-3 years ago for genome assembly. But now, because of the cost going down for long reads, they are not so interesting anymore. But yeah, it's something that one can consider for some applications. Optical mapping, so the BioNano that we used. Of course, you can use long reads as well. So a lot of genome projects around the world, they still sequence with short reads and use longer reads at low coverage to try to reconstruct a better genome from the short reads. That's a possibility. Some projects are based on that. I would not advise to do that, but it's possible and it works. Again, the quality will not be as good as if you start with long reads and use, for instance, Hi-C to generate the chromosomal level assemblies. And then, of course, these Hi-C reads. Going back to your question, why the Hi-C information can be used both for just scaffolding, so reconstruct the chromosomes, but also to separate the haplotypes. So again, with this sort of analogy of the cell and the cell nucleus that contains all the chromosomes, if you think about it as a sort of like a universe where the chromosomes are galaxies that are very far apart from each other, no, they're really separated from each other. This applies also to the chromosomes that belong to the different haplotypes. So it means that you can take advantage of this kind of information to say, well, okay, so this is chromosome 1 from the father, and it has all its Hi-C signal that is specific to that chromosome, and then this is chromosome 1 from the mother, and it has its own Hi-C signal that is specific to the mother. So if you are able to disentangle this information from the Hi-C, you can use it to also phase the haplotypes. All right. I don't know if do you know if Nadalina is sick? She wants to.
I'm here.
Oh, good.
Sorry,
no
I will
problem.
be leaving my camera off. No one needs to see me
You
sick.
sure? If you want me to, I haven't looked at the slides to be honest, but I can. Up to you.
How do you want to change the slides though? Do you want me to just let you know when? Or
I can stop sharing if you want.
okay, and then I'll share.
Yep. There you
Okay, sounds great. Just give me a moment to get oriented again.
go. Sorry, Nadalina could not be with us because she's not feeling very well, but she's still giving her malnutritional lecture.
Yeah. It's saying that maybe I didn't join the Zoom link where I'm co-host. Could you
cannot share?
access?
Yeah, hold on. Try again.
Yeah, it's going now. Okay, fabulous. Just one moment. I think this will be it.
Yep.
And okay, let's do this. Okay, everyone can hear me
Yes.
and see my screen. Great. Yeah, hi everyone. Sorry again, I can't be there today. I'm sick right now, and so I'm working from home. But I'm just going to give you a brief overview of manual curation, which follows all of the assembly that Linnell has been showing you. Is there an issue?
No, you can keep
Just keep
going.
going. Yeah, we're good.
Okay, great. So I think at the end of the salsa workflow, you should get a pretext map, and that's what you're going to be using for this. Well, actually, no, because that was a yeast genome that we assembled. And because there are intermediate files that I wanted to generate and have ready for you all, we're actually going to be looking at a different species that I curated earlier this year. It's the Heterohyrax brucei. And yeah, so we'll be looking at this, at the pretext map for this genome, and I'll show you just briefly how we go about doing curation. Yeah. So I think this has been talked about and probably touched on a couple times throughout the past couple of days, but curation is still important and relevant even as our assembly algorithms get better. So the assembly that you get out of the algorithms that Linnell showed you are very high quality already, or they should be pretty high quality. Of course, that's very species dependent and sample dependent, but there are still going to be imperfections. And so it is important that you at least try to take a look through and see if there's anything that could be manually fixed, just to make sure that the algorithm hasn't either made any sort of misjoins. So if it put pieces together that maybe shouldn't be together, or if it there were misorientations, or if there were pieces that should be put together that weren't. So I think it's a rather important step. But of course, if you're going to be doing this in your work, that's entirely up to you and might be dependent on what it is you're trying to achieve. For instance, if you don't need a super high quality assembly, then this might not be worth investing your time in per se. But just over here on the right, that is the pretext map or the contact map of the H. brucei. So you see this signal along the diagonal, and that's exactly what we want to see. But what we also see here is some signal in the off diagonal. And what that shows is that there's scaffolds interacting with each other. And those interactions are what we use to basically perform manual curation. They signify that there's opportunities for improvement in this assembly. So I already touched on these, but some types of mistakes that are very common that you'll see are missed joins. So pieces put together that shouldn't have been, pieces that should have been put together but weren't. And then scaffolds mistakenly joined. So they are perhaps put together, but then in the contact map, it shows that they really don't have a lot of interacting signal. Perhaps it was just their telomeres that were interacting, and so the assembly algorithms stuck them together. Or you might have misoriented scaffolds or pieces of a scaffold. So it might not be that the whole scaffold is misoriented, but just a portion of it, which is what you see in this image on the right here. And you can tell by this signal where the arrows are pointing. So basically that's just showing that the end of this, can you all see my mouse or no?
Yes.
So where my mouse is here is just showing that this signal here shows that this bit down here is interacting with this bit of the scaffold up here. And so that indicates that there's room to correct the orientation. Okay. Yeah, and so this is just showing that it's been resolved. And I'll show you how you can do something like that in pretext view. So I just want to reiterate exactly how much curation can help improve the quality of an assembly. So the H. brucei, yeah, again, I did this back in, I think, March or so. There were 22 breaks that we made. So that means that there were like 22 points in the assemblies in which I broke apart pieces of a scaffold or inserted something at that part. There were also 224 joins. So that means that I moved 224 things together. And then you can see that the number of scaffolds pre and post curation are quite different. So post curation, there's a significant decrease, and a lot of these scaffolds were assigned to chromosomes. You can see that the N50 increases, and you can see there's a pretty significant increase in the area under the curve as well, which is just another metric of assembly contiguity. You can also see that the number of gaps increases, and this is important to note because, of course, when we're placing pieces together, we don't know that there could be a sequence that's still missing in there, and maybe that's why the scaffolders missed it. So we always insert a gap at any join that we make. So this is just an overview of the rapid curation pipeline. The rapid curation pipeline was developed by the Wellcome Sanger Trust Institute, basically just to obviously expedite this process, even though it's still very manually involved. So what you're going to need is you're going to need your FASTA file that you generated for your assembly, as well as a pretext map, which you get out of the SALSA pipeline that Linnell showed you. There's also, I've provided the pretext map for you if you went ahead and downloaded that already. But there are also, you can also generate a HiC map with the ARIMA mapping pipeline and pretext suite on your own. And I've left links at the bottom for you to follow those instructions there. It's pretty clear once you have those, once you have the ARIMA mapping pipeline and the
Sorry
pretext.
to interrupt just to make sure, did you receive the instructions? So you were able to download the file?
They
Yeah,
were sent in an email, I believe.
It was in the email.
we can put, I'll put them in Slack, yeah.
Thanks, Julio. Okay. So once you have your FASTA file and your pretext map, the second step is to generate a TPF. The TPF is a tile path file. It's very similar to an AGP if you've seen that. It basically just details all of these scaffolds within an assembly and their location and their size, orientation, and gaps. And so you do annotate this TPF, so you will need it, but there is a script on the that you'll need for this, but it's again on the GitHub page or GitLab page from the Wellcome Sanger Trust Institute. I don't know that I have that linked here, but at the very end of this PowerPoint, there is a slide with all of the resources that you would need to do curation, and the GitLab will be linked there. So once you have that TPF, your pretext map, and your FASTA file, you're going to take your pretext map and you're going to load it in pretext view, and you're going to make edits there, and you're going to annotate any breaks you make in the TPF. Then you're going to paint your scaffolds, which again, I will show you, generate an AGP, and there's a couple of other scripts you're going to use in order to generate this FASTA file at the very end. Yeah. So yeah, again, just you're going to generate your TPF from your FASTA file. Oh, here is the link that you would need to get to that script. And here's just a view of the TPF. So if any of you have seen AGP, it's very similar. Yeah. And then you're going to use pretext view to make edits to your pretext map. And those edits directly translate into edits into your assembly via this pipeline. So let's see. This is just a view of the menu once you load up pretext view. So you're going to use your keyboard and mouse controls to navigate, and you can feel free to go ahead and do this now. I hope all of you can take a second to get pretext view loaded.
Are you able to install?
Okay, I'll just I'll go ahead because I'll leave it up. But yeah, so use your keyboard. Pretext view uses keyboard and mouse controls to navigate and to make edits to the assembly. So that's why it's so useful here, because you can actually look at the HiC signal on the pretext map and then edit on that pretext map directly. And then the edits are, like I said, translated directly out of that. And you can generate a FASTA file from there. So again, keyboard and mouse controls. So you're going to click U on your keyboard to open and close this menu that you see in the top right-hand corner. You're going to click load map at the very top there, navigate to wherever you've left your pretext file. This should be the pretext file that you downloaded from GenomeArc. And so just load that. And then once you're done, you can use U again to close the menu. Okay. Does anyone need these instructions still up, or are we like mostly okay? It's hard for me to tell from here.
Okay, so like everybody is okay.
Everyone's okay? Okay, great. So I'm just going to switch out of this screen real quick and into my free text view, and I'll show you a couple of things that you can do, and then we'll have an exercise we'll try on our own for a little bit. So I'll stop the share momentarily, and we'll go into pre-text view. So can everyone see my contact map? Okay, so I'm going to take this slow because I know for whatever reason, pre-text view can be a little bit laggy over Zoom. The other thing that you're going to have to be aware of as I'm demonstrating this is that pre-text view does have a tendency to jump around. So when you do move pieces around, sometimes you'll lose track of it, but we'll find it again. We'll just go slowly and we'll make it work. So this is a Hi-C contact map of the hetero-Hyrax brucei after it's been fully assembled and scaffolded. And so like I said earlier, what we're looking for is contiguity along this diagonal here. And then all of these pieces here, this is signal interacting between scaffolds. So for instance, this larger chunk that you can see over here, this scaffold 30 is interacting with scaffold 5. And so what we want to do is we want to move scaffold 30 and scaffold 5 together. So I'm just going to zoom in over on that a little bit. Okay, you can see it a little closer. And you're going to click E on your keyboard, and that enters edit mode. And then I should preface this. Using pre-text view is much easier if you have a 3-key mouse. But let me see if I can do it with just my mouse pad, because I'm assuming that's what most of you are working with. So you're just going to hover over this piece here that's interacting between scaffold 30 and scaffold 5. And I think, yes, you're going to click the space bar. And then you're just going to sort of move it over to scaffold 5. Sorry, it's a little bit jumpy. Is everyone seeing it moving? Okay, great. And so what we're looking for is we're looking to follow the Hi-C signal until it converges on where it approximately should be. So, sorry. So basically the white or the blue is the lowest level signal. Green and yellow are more moderate, and red is the highest signal. So what we're really looking for is for this red signal to converge on a point that suggests it belongs there. So what we can see is we can see this red signal converging here, but it doesn't seem quite right, because if you look, it's hard to move. Let me drop it here for a second. Another trick is if you use, while you're in edit mode, while you're moving a piece around, if you click S on your keyboard, that will enter snap mode. And that'll be really important, because if you don't actually want to make a break or a cut in the middle of a scaffold, then that will place it directly adjacent to whatever scaffold you're on. So this has dropped scaffold 30 directly adjacent to, sorry, I thought it was scaffold 5, or no, it is scaffold 5. That's just scaffold 4 over there. So let's drop that there for a second. We'll exit edit mode by clicking E again, so I can zoom in without worrying about clicking anything. And you see that there is this off diagonal signal here. And we want to resolve that further. So what that suggests to me is that scaffold 30 is just not oriented correctly. And so again, we enter edit mode, highlight the scaffold again with your space bar, and use the space bar again to flip it. And as you can see, it's much more contiguous along there. Just so we can see it again, I'll flip it, edit mode, space bar. If you're looking, more signal here, not contiguous through here where scaffold 5 and scaffold 30 meet. So spacebar to highlight, spacebar to flip. Now, if you do have a mouse, you can highlight this scaffold or any scaffold by entering edit mode and then clicking with the middle, with your middle click. So that's my scroll wheel basically. But I always change the orientation with the spacebar. Okay. I wonder if there's another good example I could show you. I can show you the change in orientation one as well. So this is the one that was in my slides earlier. This is scaffold 6. As you can see, there is, sorry, just one more. Okay. So as you can see, there is this diagonal.
Natalie, how do you zoom in and out again?
So that is going to be just moving up and I have a Mac, so for me that's just moving with 2 fingers up and down on my scroll pad. If you have a mouse, it would be with your scroll wheel.
How do you slide around?
You have to like hold down with 2 fingers and drag. Okay. For some reason, the chat isn't opening for me. So if anyone has issues, just shout them. I think, or if someone could monitor the chat and let me know, that would be awesome. Okay, so we're back on scaffold 6. I'm going to show you how to orient this. So enter edit mode again. And then you're going to just, pardon? Okay.
Go ahead.
Okay, great. So what we're trying to do is we're just trying to fix a signal here, right? So we want to flip this portion of scaffold approximately. The thing about doing that is that we're going to be making, this is where we would be making a break in the middle of the scaffold. And we don't really like doing that unless we know there's a gap there. So what I'm going to do is I'm going to go search the TPF for this position to see if there's a gap at this position here. Because we're also going to need to annotate that. And if there's not a gap at that position, it doesn't mean that you're necessarily wrong, but it is a warning sign that you might want to investigate that a little bit further before you make that break. So what we're looking for is approximately 47 megabase pairs in scaffold 6. So we're just going to switch over to our TPF. That's here. This one is also, this should have been available to you. I'm going to scroll up to scaffold 6, and as you can see, there's a gap basically right where we expected it to be. So 46.8 megabase pairs. So you're going to need this TPF to follow through with the rest of the rapid curation pipeline. The only thing you need to edit in this TPF is where you make breaks in the middle of scaffolds. If you're joining 2 pieces, you don't need to do anything. But if you insert something in the middle of another scaffold, or if you're like changing the orientation of just a piece of the scaffold, you need to annotate that break. And so that's just going to be this little side arrow. You're going to put that in right next to the gap, following where you're going to make the break. So that would be right here. Okay, great. So we've edited that in there. We're going to save our TPF. We're going to go back to the pretext map, which we've left over here. So once again, we're looking for about 46.8 megabase pairs. Also, the TPF can help guide your breaks a little bit better to know exactly where to cut. So if we're sliding along here, we're looking for 46.8. The thing about pretext view is it divides up an assembly into texels as well. So it might not be exactly the same number. So just get as close as you can. Okay. So now we've gone as close as we can to where we want to make the break. We're just going to click down with the left key or with just on your scroll pad. And with that highlighted, we're going to click the space bar to flip it. There's a little bit of signal still there, which I might in another instance try to get maybe a little bit closer a flip, but it also could be that this piece is interacting with the telomeres over here, and that might have been why it was misoriented in the first place. So I wouldn't worry too much about that little bit of red signal we're seeing down there. Okay, so now we flipped it and we resolved that off diagonal signal, and it's looking a lot better. So I think maybe I'll end it there and we can do a demonstration. I guess the last thing I'll show you before I click out of my pretext view is what to do once you've edited everything. By no means have we finished editing this assembly, nor will we at all today. But what you do once you're done is you're going to have to paint your scaffolds. And that's basically just grouping everything together that we've made into joins. And so we do that with this mode called scaffold mode. So you're going to click S on your keyboard, zoom in real close, and you're just going to click to highlight each piece, right? And then just hold down A. If you hold down A and you click on the farthest point from that on the next scaffold, it'll highlight everything in between. And so it's good to start at the very bottom. I'm not for this demonstration, but just to show you. And then you're just going to keep going up. So hold the A, highlight the next scaffold, so on, so forth. And now assuming you've highlighted this whole assembly, I won't do that because there's obviously 30 something scaffolds. We'll just ignore these highlights here. You enter your menu again with the U, and you generate an AGP here. So I'll just show you how to generate an AGP real quick. Go save it wherever you want. We'll just save it in here for now. The naming gets cut off on my computer. I don't know if it gets cut off on everybody's computer, but you'll just click to wherever you want to save it, rename it, and then the save button is over here. Okay. So let's leave pretext view and we'll go do, we will go do an example on our own. If I could find my, oh, there it is. Okay, great. So here's the exercise I've left for you all. I think I just showed it to you. So that's great. It'll be moving scaffold 5. And we're going to basically just move scaffold 30 onto scaffold 5. So all of the instructions are here. I encourage you all. Sorry, 1 second. I encourage you all to give this a try. If you've downloaded pretext view, let me know if you need me to go back to the instructions to load up the map again. And I think
everyone gets pretext now.
Pardon?
Everyone is pretext installed now.
Great. Okay. So does everyone have the map loaded?
I think some people have.
Great.
I see thumbs up. We're good.
Okay. Go ahead and give this exercise a try and take a few minutes. Unfortunately, it's not quite like assembly where you can leave it to run. So we'll just sit here, and if you have questions, we're here to answer them.
Madalena, can you show how you identify sex chromosomes on your?
Yeah, we could do that. Let's do that. Can we try this exercise first and then go back to sex chromosomes? What is up? Do we have a closing remark? When am I supposed to be done with this?
20 minutes.
Do we have closing remarks? We just vibe.
We just vibe. Okay. I don't know that I have another 20 minutes worth of stuff, but I mean, you guys are welcome to just play around in pretext view. It is very fun when it's low stakes. Not that genomics is particularly high stakes. Anyways.
We can cut that out of our YouTube recording. It's okay.
Oh, sorry.
Kidding. I'm kidding.
Okay. I'll just go over to pretext view again and show you how I identify sex chromosomes. This isn't a foolproof way. Sex chromosomes are very tricky, especially depending on the species. But a pretty good indication. No, it's all highlighted. Okay. A good thing is if you mess up the highlight, because it is very finicky here, this scaffold painting mode, it's annoying, and you're probably going to mess it up and have to do it a couple times over. You can just click Shift D and it will delete everything. It won't delete what you've highlighted, it'll just delete the highlight. So Shift D and it's all gone. No consequences. So a really good indication of a sex chromosome, especially if it's heterogametic, is going to be this dip in signal here. And that's just indicating that it's lower coverage, simply that there were just approximately half the reads that mapped to this scaffold, because there's only one of those chromosomes. It's usually a little bit difficult. Well, it can be more difficult to tell which is an X or a Y, or what is it, ZW in birds. But typically the X does tend to be bigger and the Y smaller. And if there's an X and Y present in the same assembly, which you'll see if you did HiFi not in Hi-C mode, just in regular mode, then you'll see a PAR region that they share. It's a pseudo-autosomal region. It's a little funky looking, but there will be signal to show that. And I think there actually is here. So we can see if we can find that PAR. If you want to double check this, if you want to double check that the coverage also dips here, you can generate what are called tracks. They're basically just like characteristics, like you would see in IGV, it's just characteristics of the genome metrics of the assembly. And so if you have those injected, which again, there are resources for it, and I have attached all of them into this slide. So if you generate coverage, which I do with GenomeCov, and generate I think it's a bed graph format, from that, you can inject it into this pretext map so that you can actually see it in pretext view. It can be a little bit difficult to see with this color, but I'm hoping on the screen it comes through clear enough.
It's clear, yeah.
Okay, great. So you can see it down here. It starts off down here. And I'll zoom in a little bit more, but not too far, because I want you to see the contrast. You can see that it dips here. There's no scale. On the side would be great. It's just not here. But you can see that it dips by about half, right? And so that's a really good indication that this is one of our sex chromosomes and probably the X chromosome. But what we do see is it goes back up right here at the very end. And I think that is probably our PAR region, or it might just be telomeric repeats, but I suspect it would be the PAR region. So let's go see if we can find that PAR region. Let's see. So we're going to go basically just along, follow that dip and signal. Oops, a little too far in. And we'll see if anything over here interacts. It looks like there's quite a few interacting pieces around here. All these pieces probably belong in there. You can see all of these pieces down here that are showing pretty strong interaction. And I think these are pieces that probably form the PAR, and they're probably connected to the Y chromosome. So let's see what that looks like when we bring it over. Yeah. So there you go. It looks like I would suspect that forms the PAR, but it would also need to move. Let's get rid of this. Let's get rid of the coverage track. Again, you just do that in the menu, click U. We're going to go into edit mode again. We'll take off snap mode because it's in that right now. When you're in snap mode, it won't let you move that along. It'll try to move it to the other end of the scaffold. So we got to take off scaffold mode. And it looks like based on the signal, we're going to be approximately moving it into here. But actually, perhaps not, because that might actually be the PAR region. What did I do here? Well, I know what keep in mind, I did do this several months ago at this point. Yeah, I think this is showing signal because it is forming the PAR. I'm not sure how I assembled it in the first place. But because it is in several pieces right now. But your Y chromosome will also show a dip in signal. I wonder if we might be able to find it down here. Let's see.
Can you comment on these small pieces a little bit?
Can I comment on what?
The small pieces in the lower right corner, like the shrapnel.
Yeah, of course. Yeah, just to, let's see. Let's get rid of the coverage here. So these obviously are larger scaffolds that you can see along here. And we call this shrapnel as just larger scaffolds that did not get assembled by the assembly algorithms, but you can see that there's still some interaction here. So not all of this will you be able to assemble. If you're looking at it, a lot of it is interacting with each other. And depending on the assembly, you might also find that it interacts with a lot of other pieces as well. And so what that typically ends up being is repeats. And repeats are, like I said, pretty difficult to resolve because they often interact at several points along the assembly. But you can do your best, right? So there's some obvious pieces here. It also could just be smaller pieces that for whatever reason didn't get assembled, but are very capable of assembling. So one good trick, because obviously there's a lot of signal along here. Like if you look along here, there's a lot of pieces that are showing pretty significant signal that can all be assembled. But one good trick to sort of make that easier on yourself and so you're not zooming in and out constantly is to try and actually move these shrapnel pieces together and sort of block them up. So for instance, you could do this one. That one moves right in there. This one as well. You follow the signal, it goes there. And that, again, up here, you'll be able to just see that signal a little bit better and see where it fits in. So if we're following along, where does that go? All right, it looks like it goes here. So it looks like it actually goes into our X chromosome. So that is that. Has anyone had a chance to try out the exercise or try moving around in pretext view themselves?
Yeah, I think they did.
Okay, great. What else can I show you or comment on? This was, I think, all I was prepared for. Let's see if there's anything else in the slides. Where was I? Here. Okay. Yeah, so pardon?
No, sorry. Leaving.
So the high-C signal is going to be sort of the foremost informant of whatever changes you make. But you can also use other supplementary data. So like I showed you, I used the coverage data to identify the sex chromosomes, but there are a number of other telomere or tracks that you can generate. So there are some tools for identifying telomeres that you can generate a bed graph from and inject as well. Also like repeat density. There are quite a few tracks that you can generate. One of the tools that we use as well, and this was also generated by the Wellcome Sanger Trust Institute, is this tool GVAL. It's very similar to IGV. I think IGV is a little bit more accessible, but our colleagues at Sanger generate the GVAL databases for us. So we continue to use that. But they basically generate this database that has a bunch of information about the assembly. And then you can, if you're looking at a particular point and you're not quite sure what to do with it in the curation, you can search for that location and go and take a closer look at some of this other data. So it's a little bit difficult. I'm assuming it's much bigger in person, but I don't know how big it is. This is telomere repeats here. There's a number of other repeats that are shown down here. You can see the scaffolds. This is coverage. This one is really interesting. It's called self-comparison. So it's basically just showing you if there are scaffolds that are interacting and which ones are interacting. So this might be helpful if the scaffolds are smaller. There's also tracks for genetic markers that you can generate, which can be helpful with some of the sex chromosomes. I know we use that quite a bit in birds and a few other taxon as well. And so, like I said, a lot of these data types can be generated in bigwig or bed graph format, and then you can follow these instructions to inject, is the term they use, into the pretext map. Sorry, one moment. Oh man, it's not coming up. And then you can open the menu in pretext view, and then under extensions, you'll find all of these tracks that you've injected, and you can view those. I've showed you painting the scaffolds. Here you can see the fully curated map. So it turns out I did resolve that PAR region. However long ago, you can see the X and part of the Y over here. And for some reason, the Y over here, which is probably a mistake from whenever I screenshotted this, but the X and Y are properly over here. And you can see that there's a lot less signal along the side. Again, you generate the AGV file. This is just a shot of the AGV or AGP. Like I said, it looks very similar to the TPF file, but it's going to detail all of the changes you made, all the scaffolds that are newly adjacent to each other, as well as any changes in orientation. It's going to retain the scaffold names, the original scaffold names, but also show what chromosomes they were assigned to. So when I should clarify, when you're painting what you want to assign to chromosomes. Everything else you just leave. Yeah. And then you can continue to follow the rapid curation pipeline to generate a final FASTA file with all of your updates. So you're going to need that AGP file, and you're going to need your annotated TPF. You're going to take both of those to this rapid pretext to TPF XL Python script, pass them both. It'll generate an updated TPF that has all the painted chromosomes in it. And then you can use that TPF along with your original FASTA file and a CSV of the chromosome names, which the previous script generates, to produce your final FASTA. And then if you really want, you can generate a new pretext map to double check that everything was changed as you wanted it to, which is what we do, but of course that's optional for you.
And sorry, just to give you a bit more detail, that the AGP really stands for a golden path, and really defines a path through contigs that define the final scaffolds in your. So it's a file format that has been invented, I guess, ages ago to define a scaffold made of a series of subcomponents, which are the contigs.
Exactly. So, yeah. And then that's pretty much it. That's what I have for you today. But I also have a number of supplementary slides back here because we just simply cannot curate a whole assembly in a day. So here, there's a number of examples back here, as well as how to annotate the TPF accordingly, how to use GVAL if you're interested in doing that. We generate our own GVAL databases, but there's also publicly available GVAL databases. Again, IGV is a very good substitute, and I know that's more popular. And then here is the list of curation resources that I was talking about. If you are interested in curation, I know this is quite a bit, but I implore you to go through them. I promise you will probably find what you're looking for. And also you're welcome to reach out to us. And I can even add you to a Slack group called Assembly Curation, where you are welcome to send your questions to the general channel. And there's a lot of people in there that will help you, as well as myself. Anyways, thanks.
Any questions?
Yeah, Nadolina, how many genomes can you curate per week?
Oh, at least 30 daily.
Oh, daily.
Anyway, not that many. It's slow. And once you get used to it, it's slow to start. It's probably always going to be slow because it's a very manual process. And every
Truly, it's a joke. We're not.
Oh, I know. I was just giving context for everybody. It might also help whether or not, help them decide whether or not they want to curate on their own. Because every genome has issues. So it's always going to be slow. But it's important if you want a high quality reference genome. So we continue to do it.
All right. Well, thank you so much, Delina, and hopefully you feel better soon.
Okay.
So just to recap, so you start out, you try to infer properties of the genome without first assembling it, then you assemble it, but usually don't get a complete assembly that has all the chromosomes telomere to telomere reconstructed. So you scaffold it, and still, because it's automated algorithms, you have a few issues left or several issues left. And then manual curation can help fix some of them, and then you're done. So you submit to the public archives, and hopefully also publish your own genome. So with that, I think, hope you enjoyed this. Again, we are always open to any questions you may have, so feel free to reach out. If you have, I don't know, your own project you wish to discuss, that's also interesting. And yeah, that's pretty much it. So thank you for staying with us. It's been a long couple of days, but yeah, thank you so much. And likewise, everybody online, thank you for bearing with us.
Grab some food on the way out.
Yes.
So much food.
No, we're not